this up. Hey there, B. Let me know if there's anything that goes well. It's great to see you. Hello. Kind of a different setup today. All right, we're going to see how well this thing goes. And we will be starting in just about like 30 seconds. We're going to see how well this goes. Nice, you got a 51. Heck yeah, V. I got stuck on a lot of visualizing for non-calculator MF. Gotcha. Well, we are going over the non-calculator multiple choice first, so hopefully it'll be going a little bit well. We're going to start off our live stream. We have a timer in the left-hand screen with the slides and all of the questions up on the top left-hand corner. We'll be going through each of these questions today. You'll always be able to look at what question we're on by just looking at the top left-hand corner. The speed run will basically be going through each of the non-calculator multiple choice questions first. Those each have like a 2-minute and 50-second per question kind of setup. And then the calculator section will have like a 3-minute per question kind of setup. After that, we'll go over our 4 multiple choice sections. For those 4 multiple choices, those are each going to be 15 minutes each. In just 1 second, we will be beginning our full live stream. Thank you very much for tuning in. Just getting a drink. And without further ado, let's make sure the pen shows up. Cool, cool. All right. And we'll see how this goes. Imagine you guys are like taking a seat for the actual problems themselves. And you're starting in 3, 2, 1, and begin. So for our first question here, we're taking a look at the actual booklet itself. So for question 1, we just have this here. So first question itself, the polynomial function p is given by p of x is equal to negative 3x to the 7th power, that whole equation there. Which of the following statements about the end behavior of p is true? The sign of the leading term of p is positive. Well, we know that the leading term here is negative 3, so we know right off the bat that this is false. Let's make sure that our thing is all set up correctly. There we go. Now we're good. So we know that that leading term is negative. So we know automatically that A is wrong. Same thing with B here, or same thing with C here. We know the leading term is negative, so the leading term of P is positive is false. But let's continue with that first statement. And the degree of the leading term P is even. Therefore, this limit as P of x approaches infinity, as x approaches positive infinity, P of x goes into positive infinity as well. We know that since the limit up here is odd, we know that this is going to be wrong. So we know that it is negative. So B and D look right. We know that it's odd. We know that this is odd. So we can cross out C. We can cross out A here. We now just want to take a look at the differences between these limits here. And for these limits, we want to try and imagine what this equation does as x increases without bound. We don't really care for P of x. We don't really care what the other terms are. We just care about what the largest exponent is. So we can treat P of x as this equation as negative 3x to the 7th power. Since it is negative, as x is increasing to the limit of x increasing to negative infinity, that negative number is being multiplied again and again and again. So then you'd get this negative number multiplied 7 times, which is a negative number in the end, times another negative number. So you're multiplying a negative number 8 times, an even number of times. So we know that as x approaches negative infinity, p of x will approach positive infinity, not negative infinity. So for problem 1, we know the answer here is going to be D. Moving on to that next question there. For problem number 2, the depth of water in feet at a water hazard on a local golf course is modeled by the function d. The graph of y equals d of x is shown for that interval of 0 to 30 for t, when t is a number of days since the first day of the month. What are the intervals of t on which the depth of water is increasing at a decreasing rate? So it's this increasing at a decreasing rate that we want to try and determine for this area here. We can kind of break up this graph into a few parts. For this first part here, we're able to say that it's starting at some value here, and we know, absolutely B, that anything that is increasing at a decreasing rate is going to be concave down. So all of this section in red here, going from this x equals 0 all the way up until about 9 here, we know that this part of the graph is increasing because it's going physically up higher, but this rate itself, if we make these little tangent lines almost on the graph itself, so make a little tangent line here, make a little tangent line way up here, we can see that the rate, the average rate for this slope to this slope is going clockwise, or going more, or decreasing almost. So we're going from this larger slope to this lesser slope. So this section here is increasing at a decreasing rate. Now let's just see if there's any other intervals where it's increasing at an increasing rate, because we know that from 0 to 9 here, we know that that's the case. So if we go from this interval from 9 up until, let's say, maybe 24-ish, between like right here, the graph is also concave down, but this is decreasing at a decreasing rate, because the tangent line at like earlier on in the graph, this here, is still going in this counterclockwise motion, so it's decreasing as the graph is continuing on this x-axis. And then from like x equals 14 to x equals 30, that graph looks vaguely concave up. So technically speaking, this section of the graph is decreasing, so it's still going down, but it has this increasing rate because the average rate of change at this part of the graph is actually slowly going counterclockwise, or it's like it's increasing. So for this purpose of the question, what section of the graph is increasing at a decreasing rate? It's not going to be between 9 and 21. It's not going to be between 21 and 30. So we know D and C are also wrong. So the only answer in this case is going to be A. So we're going to move on to our next question here. For this third question, taking a look at 3, we're going to let f be a function with the domain of -6 to x to 12, where the function of g is defined by g of x is equal to 4 times f of x of 2 times x plus 3 minus 1. For this problem itself, we just want to try and plug in the values here that are affecting x into this equation for g of x. So we know x is between -6, which is less than or equal to x, which is less than or equal to 12. We can make that new equation of -6 is less than or equal to 2 times x plus 3 is less than or equal to 12. And then we just solve for x for that interval. So basically we're multiplying or dividing both sides by 2. That divide by 2 goes into both of these sides. And we get negative 3 is less than or equal to x plus 3, which is less than or equal to 6. And then we subtract 3 to all three sides. We end up getting this interval of negative 6 is less than or equal to x, which is less than or equal to 3. And then for this interval itself, this one's going to be our answer for C. So we kind of saved a little bit of time there. We're able to move on to that next question for number 4 here. For number 4, the table above. So there's a question in the chat where it is, so the x, you just plug in what is in the brackets because that is what affects the horizontal stuff? Absolutely. So in problem 3 real quick, looking back at problem 3, we just want to plug in what affects the actual x value for the domain of f here, because that's what's going to affect the domain of g here. So all we really do is plug in these elements that are affecting the inside function of f here. That's going to affect our domain, which affects the output of f of x, which is the now new input for g of x. So like V was saying, we just plug in this 2x plus 3 into that inequality and then solve that inequality there. If we take a look at 4 though, 4 is asking us about this table. The table above gives the values for function h as selected for values of x. What is the average rate of change of h over the interval of -1 through positive 7 here? So all we want to use that pre-calculus average rate of change equation, which is f of b minus f of a all over b minus a. So f of b in this case is going to be this second value here. So we know that when x is 7, our h of x is going to be 5. So we're able to plug in 5 minus, well, when x is -1, h of s is going to be -4. So we plug in -4 here. And then our original b value was x is 7. And then our original a value here is x is -1. And then we find that we get 9 over 8. We can't really simplify this fraction, but luckily 9 over 8 is one of our answers here. So we just plug it in. That's it. Moving on to problem number 5. Just blazing through this test right now. For 5 here, the function f is given by f of x is equal to x to the third power plus 2x squared minus 8x. And the function g is given by g of x is equal to x squared minus 7x plus 10. Let h be this given composite function where it's going to be f divided by g here. What are the intervals where h of x is greater than 0? So first, let's just kind of make this little line graph where h of x is either positive or negative above or below that x-axis. So we know h of x here is actually equal to that composite function of f of x divided by g of x here, which is equal to x to the third power plus 2x squared minus 8x all over x squared minus 7x plus 10. Let's kind of factor this just a little bit. At least in this top section, I know each of these terms here have an x value that I can pull out. So I can say x times x squared plus 2x minus 8 all over. Well, let's factor this one out. We can use that cross method. Two numbers that multiply to 10 but add to -7 is going to be -2 and -5. So we can say x minus 5 times x minus 2 in the denominator now. Let's factor out this top section here. So we just want to use that cross method again to solve what multiplies to -8 but adds to 2. That's going to be -4 and positive 4 and then -2. So we end up getting the numerator of x times x minus 2 of x plus 4 all over x minus 5 times x minus 2. So we can factor this out a little bit, taking rid of those x minus 2's. Now we can start plugging in some of these values for the zeros of this equation, meaning that we know h of x is going to be equal to x times x minus 4 all over x minus 5. In this case, we have these two zeros in our equation here with this vertical asymptote in this equation here. So we know that in general, across all of these values here, we're going to have 4 either zeros, holes, or vertical asymptotes for this equation. So that number line basically looks like this, where we have a 0 at x equals positive 4, positive 4 here, so there's a 0 at x equals negative 4 here. There's a 0 at x equals 0 here. And then there's going to be a hole at x equals positive 2 from the hole that's right here. And then there's going to be a vertical asymptote at x equals 5. So we just want to see when h of x is either going to be above or below the this x-axis. And we just plug in some number between or past these intervals here. So if we plug in -6 into this equation down here, -6 would be a negative here, a negative here, and a negative here. So 3 negatives gives us a negative down here, and a negative down here. So that gives us a positive. A negative divided by a positive would give us a negative value. Between -4 and 0 here, if we plug in like -1, if we plug in -1 here, that would be a negative value. -1 here would be a positive value. -1 here would be another positive value. So this negative times a negative times a positive would be a positive. -1 in this x value, -1 minus 5 would be negative. -1 minus 2 would also be negative. A negative times a negative would be a positive. A positive divided by a positive gives us a positive value. And all I'm doing is I'm taking this interval here of 0 to 2, and I'm just going to plug in 1 into x into this equation here and imagine what it does. So positive 1 into this x gives me a positive 1. Positive 1 in x minus 2 is going to be a negative value, so a positive times a negative. Positive 1 plus 4 is going to be a positive value, so a positive times a negative times a positive would be a negative. Positive 1 minus 5 here is a negative. Positive 1 minus 1 is also a negative, so a negative times a negative is a positive. So a negative divided by a positive is going to give me a negative value. Usually what happens between these intervals here is between each of these intervals, you usually see a flip in polarity. So it goes like negative, positive, negative, positive, negative. However, if we plug in like positive 3 into this equation here, positive, 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 negative, positive down here, we end up getting a negative in this case. That's because at 2 here, it's actually just a hole, so it's not crossing the x-axis. Same thing when we plug in 6 here. 6 would be a positive, 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 positive. So positive divided by a positive is going to give us a positive here. So when is h of x greater than 0? Well, it's going to be between -4 and 0, and anything past 5 here. So our answer in this case is going to be B. Good to move on to that next problem now. Going to make up a little bit of time in problem 6 and 7. For problem 6 and 7 here, we're given this problem of which of the following functions has a graph in the xy plane with a 0 at x equals 4, a vertical asymptote at -1, and a hole at x equals 3. Well, we know holes at x equals 3 mean that the function itself needs to have this as a 0 in both the numerator, so x minus 3, and the denominator x minus 3. So for these here, let's try and factor these out real quick. We're given this -3 times 2. So this -3 times 2, numbers that multiply to -3 but add a -2 are going to be x equals 3 times, or -3 to 2. That would be positive 3 and -1. So then -1 over x plus 3. In this case down here, 12 and -7 multiplied to 12, but add -7. That would be -5 times 2, no. 3 times -4. There we go. So we get x minus 4, x minus 3. So in this case here, we have an x plus 3, x minus 3 for this first problem, so we don't have that. For this one here, we have that in this previous denominator is now the numerator, So this is equivalent to x minus 4, x minus 3. This bottom part is now the denominator here, but it's a negative 2. So this is going to be negative 3 to negative 2. So that's negative 2 to negative 1. So we'd end up getting x minus 1, x minus 2. In this case here, we don't have a denominator and numerator that match each other for negative 3 here. However, let me do this real quick. That gives me actually, this factors out a bit differently. Let me see this real quick. Actually, this is wrong. It should be negative 3, negative 2, then we get negative 3, and then plus 1 here. Yeah, there we go. So this is a plus 1 minus 3, so I actually did this incorrectly. So we do actually have that negative 3 in the denominator and numerator in this case here. I refactored this out. So we do have a whole at x equals 3 in this case. We also happen to have a 0 at x equals 4, which means that you can solve out one of these parentheses only in the numerator instead of the denominator. So we have that here, and we have a vertical asymptote at x equals negative 1 because we have this x equals positive 1 down here in parentheses. And since that isn't in the numerator, this also creates a vertical asymptote. So we know B is going to be the answer for number 6. We're going to move on to that next problem here. For that next problem of 7, we're given this table above, gives the values of a polynomial function f at a selected values of x. We're going to let g of x equal a times f of b of x plus c, where a, b, and c are all positive constants in the xy plane. The graph of g is constructed by applying 3 transformations to the graph of f in this order. A horizontal dilation of a factor of 3. So we know that's going to be something that affects our b value here by having 1/3. It's that inverse effect. A vertical dilation of a factor of 2. So we know that vertical dilation is going to affect our a value by being times 2 in front of it. And a vertical transformation of 7 units here. A transformation is just when the constant at the end is just being added or subtracted. So we know that constant is going to be 7. So what is the value of g of x? Well, so g of negative 7 here is just going to be what f of x was at negative 6. So we have f of x here at negative 6. And now we can say that g of x here is equal to 2 times that f of x of 1/3 times x plus 7. And all we really want to do is plug in negative 6 into where this x is. So now we just do g of x is equal to 2 times f of 1/3 times negative 6 plus 7. That gives us negative 2. So f of x at negative 2 is going to be 4 here. So now g of negative 6 is equal to 2 times 4 plus 7. 2 times 4 gives us 8, plus 7 here gives us 15. So we know that g of x equals 15. So we know our answer for this one is going to be D. Moving right along, so we make our time here to 8. For 8 now, we want to try and solve out this decreasing exponential function. The values of the term of this geometric sequence, g of n, are graphed in the figure above. Which of the following is an expression of the nth term of this geometric sequence? So what we want to try and identify is this g of n is going to be some a value times the rate to the nth power. We can see that between each of these values here, it's getting halved, because up here for the y value, it happens to be 12. Then the y value becomes 6. Then the y value becomes 3. And then this y value becomes 1.5. So we can say that this rate for this problem here is going to be 1/2 here. So we can say that if this is a1, our a1 is when x was equal to 1 here. So we're able to identify that since our a1 isn't listed, but our a2 is listed, we can use this g of n is equal to a of n times r of n minus k. K in our case will be 2. So we can say g of n is going to be equal to 12, because 12 is going to be when a equals 2, times our rate of 1/2 of n minus 2. So we're looking for something that looks like this equation for this here. We know our rate's going to be 12, so we know b is going to be the case for this. We have 12 here, 12 here, 12 here. We have a rate of 1/2 for all 4 of these, but the only one that has the correct exponent is going to be c. So we're able to say c is for this geometric equation, because we found that a of 2 was this x of 2 was the first actual listed point on the actual graph. Moving on to our next question here for question number 9. Question number 9 states that the value of a new AI technology stock is modeled by the function t. The value of the stock is expected to increase by 16% each year at a time of t equals 0 years. The value of the stock was $382. Which of the following expressions gives the value of the AI stock after m months? Note, there are 12 months inside of this year. So really we just want to try and find a of t here. For a of t is broken up into some a value, some rate value, and then some exponent here. Since we know that the rate is going to be in 12 months, we know that this exponent should actually be the m, which is the number of months, divided by 12, because we're looking at it from a yearly perspective. This m times 12 would be the inverse of that, so we don't want these m times 12s. We only want these m divided by 12s. So we know that b and c are out of the running. We now want to identify if this rate of 0 or 1.116 or 0.16 is going to be for our answers here. Since we know that we're increasing by 16%, if we were to multiply out for this equation here, if we keep plugging in some value for m and then multiplying it over and over again to this decimal here, we get some function that decreases over time, similar to the equation before it, where this rate was some fraction, some decimal, and we get this function that decreases over time. Since we want to increase over time, we know the rate here of our rate has to be above 1 for it to be increasing, so we can say A is going to be the answer for 9 here. We're now moving on to 10. For problem 10 here, we're going to be given this table again of f of x and g of x. For 10 here, the table above gives values for the function of f and g at select x values. Functions f and g are defined by all real numbers. We're going to let h be this composite function defined by h of x is equal to f of g. What is the value of h of 3? So all we really want to find is h of 3 is equal to f of g of 3. So our first goal is to find what g of 3 is. Well, g of 3 is when x equals 3. G of x is equal to -2. So really we're trying to find h of 3 is equal to f of -2 because our g of 3 equals -2. Well, f of -2 is just when x is equal to -2. Since x is equal to -2 here and f is equal to 5, we know h of 3 is equal to 5 here. So our answer here is A. Saved a little bit of time for that problem there. Moving on to problem number 11. For problem number 11, we're given this weird-looking graph here. For this weird-looking graph, we're asked to find that the figure shows a graph of a polynomial function g. Which of the following could be an expression of g here? Well, since we're given a value here that has not just 1, not just 2, but 3 zeros, we know that we're looking for something that has 3 different binomials here. We have 2 binomials here that are positive, so we know that our parenthesis binomials would have like an x negative, 2, and then like an x negative 5, because this 0 would then give us like an x of 2 and like an x of 5. And then we have a 0 here of like a negative number. So we know this would be like an x plus 5 in this case. And now these numbers of 5, negative 2, and negative 5 are all made up, but more so that this is like a negative binomial and this is like a negative binomial to get these two positive zeros. The unique thing about this first 0 here is that the graph is just barely kissing the x-axis, just barely touching it. So we know that this 0 here has to have an even exponent. So 2, 4, 6, or 8. We know that each of these zeros here have to have an odd exponent of some kind. We also know that if we ever have a graph where there's a point of inflection at the 0 here, like this graph here, which is decreasing at an increasing rate, to this graph here, which is decreasing at a decreasing rate, if the point of inflection occurs at the 0 here, then we know that this binomial would be something to the third, fifth, or sixth power. So not just odd, but at least to the third, fifth, or sixth, or sorry, third, fifth, seventh, so on and so forth. So what we're trying to find is some binomial that has an even exponent. So we want to look down here at our problems here. So we can see that for our problem here, this binomial here has a 2, but it's a positive 3. So you know A is not going to be the case. We know for C, there's nothing that has a 2 or an even exponent, so we know C is not the case. Same thing for D here. In case of B, we have that even exponent to a binomial that has a negative value inside of it, so this would create a positive constant. We have a second binomial that would create a positive 0, and we have a third binomial that creates a negative 0 here, so you know B is going to be our answer for problem 11. Moving on to problem 12 now. For problem 12, we have a little bit of time to spare, so we can kind of take a look at these questions more in depth. For problem 12 here, we're going to let k, w, and z be positive constants, which of the following is equivalent to log base 2 of kw to the third power of over z. Well, we want to try and use some log properties to try and expand out this log. We know any logs that are being divided inside of its argument really are just two logs that are subtracting each other. So we can say log of base 2 of kw to the third power is equivalent to minus log base 2 of z to the second power here. And now we want to try and do something with this second to the z here. We know that there's this power property for logs where if there's an argument that has an exponent with it, we can just pull that exponent out and create it as like a product or like a coefficient. So we can do that again here after we separate these two. Since these two are being multiplied, we know that k and w are just being added to each other. So this expands out to log base 2 of k plus log base 2 of w to the third power minus 2 times log base 2 of z. We can do that power property one more time with this w to the third to get this fully expanded out as log base 2 of k plus 3 times log base 2 of w minus 2 times log base 2 of z. And in that case there, this matches our problem for B. So you know 12 here is going to be B. Moving right along to 13 now. For 13, we're able to say that a polynomial function p is given by p of x is equal to a times x to the nth power plus 5 times x squared minus 3x minus 2, where a and n are constants and n is greater than 2 here. Which of the following could be the values for a and n? If the n behaviors of p is as x approaches negative infinity, p of x goes to negative infinity. As x approaches positive infinity, p of x still approaches negative infinity. So for this problem here, we're able to say that the graph of p of x looks something along the lines of this, whereas x approaches negative infinity, it goes to negative infinity. as x approaches positive infinity, it also approaches negative infinity. So now we need to determine what the graph does inside of this problem here. Since we know that n is going to be some positive number that is greater than 2, so n can be 3 or 4, 5, 6, or 7. We know that n here for this b value can equal 2, so you know b is automatically wrong. We now want to try to figure out what p of x would do for this function of a times x to the nth power, where if we want to make these two constant values here, we know that a here has to be some negative value because we want the n's here to go down to negative infinity. So we can get rid of this option here for a is positive 4. Same thing here for b, but we already crossed out b, so we know it's not going to be a. So we want to have these negative values here for a. So negative 3 works for both c and d here. However, we know that it's not going to be some odd number for n here, because an odd n would give us an odd exponent, and we know an odd exponent creates these green graphs here, where one tail is going to go to positive infinity, while the other tail would go down to negative infinity. So this is true for odd problems. For even problems, we know that even problems, the tails go in the same direction. So we know that n has to be either 2, 4, 6, or 8. So if n was 4, it would create some kind of wave that looks like this. And we can say d is 413. At this point here, we're going on to problem 14. Problem 14 marks our halfway point for the non-calculator multiple choice here. So we are well in our way to completing this exam on time. We should complete this question here with 40 minutes still on the clock. So we still have like 3 extra minutes to kind of burn. For problem 14 here, we're going to let k of x equals 4 times this rate of 1/3 to the x power. Which of the following statements about k is true? Well, for k here, we know that this graph looks something along the lines of this, because we have this rate where the rate is less than 1. So we're going to have this decreasing graph. So we know x is decreasing, not increasing, because we have that negative rate. And now we just need to figure out if it is decreasing and concave up or decreasing and concave down. Well, a graph that is decreasing and concave down would look something like this, like a reverse logarithm graph. And these here would be like negative log graphs. These are not going to be, or these graphs here are going to be some positive exponent graph where the rate here is less than 1. So we know that a is going to be our decreasing and concave up for this graph here. For a decreasing concave down, it would be like a negative log graph. So we'll say for 14, it was going to be our problem for a here. Now that we are done with 14, we are halfway done with 4.5 minutes to spare. So now we are good to try and take our time with the second half of this multiple choice. For the second half of this multiple choice, we're looking at problem 15. For problem 15, the function of h is given by h of x is equal to sine of beta plus pi over 3, where beta is between 0 and pi over 2. Which of the following are equivalent forms of h of x? We want to try and rewrite h of x here as some product of sums. Since sine here is two angles here being added together. We know that sine of alpha plus beta is just going to be equivalent to sine of the alpha times cosine of beta plus sine of beta times cosine of alpha. And this gives us the equivalency of whatever this would be. So to write out this problem here, we're able to express this sine of beta plus pi over 3 as sine of beta times cosine of pi over 3 plus sine of pi over 3 times cosine of beta. And now we're able to simplify these out. Well, we know that cosine of pi over 3 is going to give us 1/2. And we know sine of pi over 3 is going to give us root 3 over 2. So we can say this gives us 1/2. We can say this gives us root 3 over 2. And all of this as an equivalency would just be 1/2 of sine beta plus root 3 over 2 cosine of beta. And in this case, this here is exactly what A is. So we know 15 is going to give us A. It's important to know this kind of connection here for this sine equivalency. This is also the same kind of thing on if sine was alpha minus beta. The only thing that would change is that this minus here changes to a negative here. We now want to look at 16. For question 16, a polar function is given by r is equal to f of x is equal to cosine of theta, f of theta is equal to cosine of theta minus 1. As theta increases on the interval of 0 to theta is less than pi, which of the following is true about the points on the graph of r is equal to f of theta in the x and y graph? For this here, we know that our cosine of minus 1 in polar form is going to give us some equation where we know cosine in polar form gives us one of those little leaves that goes to the right-hand side of this x-axis here, where our y and x in polar form for this cosine here is just going to be our normal cosine of theta graph here, but it's moved down 1 unit because of this minus 1. So you know our x and y graph actually looks like this for this equation here. So for A, the points of the graph are above the x-axis and are getting farther from the origin. Well, we know that they're not above the x-axis because the graph of cosine of theta is shifted down 1. So we know it shifts from this graph to this graph. They're not above the graph, so A is wrong. The points on the graph are above the x-axis. Well, we already know this is wrong. And are getting closer to the origin. Well, we know this is wrong because we know the cosine graph is leaving the origin in the right-hand side. So we know B is incorrect. I'm going to skip over to D. D, it says that the points of the graph are below the x-axis, which is correct. C also says the same thing. And are getting closer to the origin. Well, we know that's wrong. We know they are going away from the origin. So C is going to be right for problem 16. Finish that with problem 16. Now moving on to problem 17. For problem 17, what are all values of x for which, what are all values of x for which natural log of the root of x minus 5 is equal to 2? For this problem, we just want to try and honestly solve out this equation here. To solve out this equation, we're given ln of the root of x minus 5 is equal to 2. To get rid of any log function like ln, and as a reminder, ln is just the log of that very special number of e. So really this is just ln of the root of x minus 5 is equal to 2. To get rid of any log function, we just raise this whole side to the exponent where e is to that base. So really for this here, we're saying e raised to the power of this whole side, e raised to the power of 2, and we end up getting the root of x minus 5 is now equal to e to the square root, to the squared. If we now square both sides to get rid of that root, any exponents to another exponent, you're just multiplying those exponents together. So we end up getting x minus 5 on the left-hand side, e to the 4th power on the right-hand side, because these exponents multiply to 4. And then we just add 5 to both sides to get x is equal to e to the 4th power plus 5. So now we solve this out. We know D is wrong. In this case here, it's trying to say anything along the lines of like if e can be negative and positive. In this case here, we didn't square root e in any of our steps, so we wouldn't have like a positive and a negative of it. So we know C is wrong. I have no idea what this x of equals 9 here is, so I'm going to cross out A. And the only thing that is right is this e to the 4th plus 5 here. So we know B is going to be right for problem 17. Thank you very much, V. I appreciate the little hundreds. Moving on now to problem 18. Since we are significantly ahead of the test right now, if you have any questions on the AP exam, please let me know. You can fully pause and go back to that problem. For problem 18 here, the sales department of a fishing supply company is estimating projected sales data for a new saltwater fishing reel under development. The sales analysts uses a linear regression to create a model for the sales over time. The figure above shows a graph of the residuals of a linear regression. Which of the following statements about the linear regression is true about this model? Well, looking first at this model, we can kind of see this pattern where these residual amounts form this upside down U. So we know that this regression model doesn't fit the projected data because we have a pattern that emerges. For this pattern here, we want to identify that this is not an appropriate model for this problem because it forms that pattern. So we know that this is not an appropriate, so we can get rid of these appropriates here. Let's also look at C and D for other wrong statements. So for D here, the linear model is appropriate. We know it's not appropriate because it forms a pattern. Because all the residual models are a relatively small size, that the size of the residual models doesn't really have anything to do with it. The relative size is talking about this distance from the quote-unquote x-axis for this problem here. We know C is wrong because the linear model is appropriate because there is a clear pattern in the graph of the residuals. Well, if there is a clear pattern, then we know it's not appropriate, so C is contradictory. B here, the linear model is not appropriate because the graph of the residuals is not a linear pattern. The not a linear pattern here has nothing to do with if a graph is appropriate or not. We don't want to have any kind of pattern form on our residual graph. We really want our model to have something that looks like this, where all the points are clustered around the x-axis. The only thing that's right is A, because A states that a linear model is not appropriate because there is a clear pattern in the graph of the residual models here. Now we're going to look at the problem 19 here, as long as there's no questions. V, I totally believe in you. You can totally finish this within 45 minutes. It's so easy. For 19 here, we're going to burn through 19. 19 is going to be another composite kind of problem where f of x is equal to 1 plus 4 of cosecant of x is equal to g of x is equal to negative 7. In the xy plane, what are the x coordinates of the points of inflection of the graph of f and g for 0 to 2 pi? For this problem here, we can kind of write out when these two equations actually equal one another, and that would be when they happen to intercept. So for 19 here, we really just want to see when f of x is equal to g of x, because that's when they happen to intersect. So all we're saying is when f of x is equal to g of x, we get this equation of 1 plus 4 cosecant of x is equal to negative 7. We can solve this out a little bit by subtracting 1 to both sides. And then we're getting 4 of cosecant of x is now equal to negative 8. Divide by 4 on both sides. Cosecant of x here is now equal to negative 2. We now want to try and find when cosecant of x is equal to negative 2. Well, I don't really know anything about cosecant. Cosecant is kind of weird to me, but I do know that cosecant is equal to 1 over sine. So if I know that cosecant is equal to 1 over sine, I can actually just take the whole reciprocal of this equation here. So if I flip this whole equation, I actually get, cosecant of x is actually equal to 1 over sine of x, which is also equal to -2. And I can flip this whole equation to say sine of x is equal to -1/2. Right? I'm basically taking the reciprocal of both of these sides here. Well, when is x equal to -1/2? Well, x is equal to -1/2 at 2 points in our unit circle here. It's going to be when our when our points here are like negative. So we get it at 1 here and 1 here for the sine values. So we know sine is going to be equal to theta of 7 pi over 6, and its corresponding value over here is going to be that 11 pi over 6. So since we made this equal to each other, we then flipped our reciprocal to get sine of x is equal to 1/2. We know that sine of x is equal to 1/2 at these 2 points, making our answer here D in this case. And all these values here are just incorrect. We can come back to this problem after we finish the rest of this non-calculator section here, if you'd like. But this is the only weird part was flipping both of those sides at the very end here. Once we're at this point, I feel pretty confident that students can find when sine of x is equal to -1/2. We're going to move on to question 20, as long as there's no questions about 19 or those beforehand. For question 20 itself, which is the graph of f of x is equal to 2 plus 4 of sine of theta? When we know sine of theta here for polar form creates one of those graphs that are above the x-axis. So they look like this. These are like sine of theta graphs in polar form. So we can get rid of A, we can get rid of C. We know A and C are going to be some cosine of theta graph here. We also know that the for this +2 value here changes the size of the ring that's inside of it. So this +2 is going to be this 2 here, and then the distance from 2 to the outer edge here is 4, which is where this 4 is coming from. So our answer for this one is going to be D, because 2 controls the size of that little inlet, and then 4 controls the distance between that top of the inlet to the peak of the inlet. For polar functions, these were honestly barely covered in our class, so we kind of played around with it. Notice for this problem here, this is the only time where this is going to pop up. So if you would like to play around with polar functions, I highly suggest you guys just start plugging in equations that look like this into Desmos into polar form and just kind of see what they look like. I believe there will only be like 1 or 2 questions that will look like this on the actual AP test. I wish we covered this more often in our class, but we just never got to it at the very end. Anyways, moving on to 21 here. For 21, we're given this problem where the number of people standing in line to cast their vote during the lunch hour can be modeled by the function of v, given by v of t is equal to 49 minus 23 cosine of this. I'm going to pause 1 second. Yes, in the chat, sine is on the y-axis for this previous question here. I want to answer a question that popped up in the chat. Yes, so these 2 graphs here are going to be sine of theta in polar form because they're on the y-axis. We know these 2 equations here are going to be some cosine of theta graph because they're on the x-axis itself. As for the A and C value, and then cosine on x-axis, like A and C, yes. So cosine is for the x-axis here, sine is for this y-axis here. The other thing for the loop itself is that it goes to 6 based off of this C value and this B value here. All you really do is you take this value here, add and subtract that B value of 4, and then this gives you that 6, 2. This 2 is these top inlets that are right here and here. So this gives you plus this, that's polar graph. The smaller number is the bottommost loop for your bottom graph here. Looking, back at 21 now. For 21, where t is the time since lunch began in minutes, for t is between 0 and 60, which of the following is the maximum number of people waiting in line to cast their vote? For this here, we know that the value of 49 is our constant, so our value of 49 is starting at 49 here. And theoretically, the highest number that cosine could be for this argument here, the largest number that this term could be would be like between -1 and +1 here. So these are going to be the extreme values that we can plug in to see what our largest and lowest value for v of t would be. So ignoring everything for t, right? It doesn't matter if t can be between 0 and 60. The largest that this cosine function can be is between -1 and 1. So really, we're looking at v of t is equal to 49 minus 23 times -1, or v of t is equal to 49 minus 23 times +1. In this second case here, this negative number times this positive number creates this difference here. So we'd get some small value where v of t would equal like 26. And that's significantly less than if this was -1, where we get 49 plus 23, which would we get 72. So this is going to be the highest number that we can get, which is going to be b. So for this problem here, I want to recover it just for a second. We don't even need to look at what t can be. The reason why we don't need to know what t needs to be for this case is because this cosine here can only be as large as 1 or as small as -1 here. So we're now able to plug in these values for this whole term, and that's what we did here to figure out that the best case is when cosine would equal -1, and we would get v of t is equal to 72. There's a question in the chat, Geyser, if I got 5, can I do a backflip? I cannot do a backflip if you get a 5, but if you do get a 5, I'll be very, very proud of you. I'll be very proud of any students that get a 5. If you just follow everything that we do on this stream here, you get 100%, so just do it that way. So we get B in 21's case. We're good to move on to 22. At this point, we are significantly ahead of the clock, so we're like nearly 5 minutes ahead of the clock, so we are straight chilling. Moving on to 22 for this problem here. Point P has a polar coordinate of -4, 2 pi over 3. Which of the following coordinates is equivalent representations of point P? Well, what we want to try and do is identify where this -4 and this 2 pi over 3 would be on our unit circle. So for our unit circle itself, we'll have this setup where our x-axis and y-axis go like this. We'll have a circle that has a radius that is equal to 4 here. And we want to go 2 pi over 3 around, which would land us somewhere over here in the unit circle. So we know that 2 pi over 3 lands somewhere in this second quadrant here, because the first value here is going to be 0. And then over here is going to be pi. Up here is going to be pi over 2. Down here is going to be 3 pi over 2. And we want to try and find some equivalency points for these sections here. So an equivalency point would be at -4, 2 pi over 3. We have this equivalency point down here, and we can find either by making this first term negative and then adding a pi to this, or keeping this term as negative or adding 2 pi to this. So a point P, which is -4, 2 pi, is the same as some point P still at -4, but we've added 2 pi to this problem here. So if we added 2 pi to this coordinate, we'd get plus 6 pi over 3. So that'd be 8 pi over 3. We can also subtract 2 pi from this and keep this as a -4. So we could get some point P as negative 4, this minus 2 pi, which would be negative 4 pi over 3, and these, all three, would be the same points. However, if we want to change the polarity of this r value here and say we want to be P of positive 4, well, this positive 4 here would then be equivalent to this plus or minus negative pi. So then this plus positive pi would just be 3 pi over 3, which would be 5 pi over 3, and it could also be subtracted by a pi. So we can get positive 4 of negative pi over 3. And then, so this point here of negative 4 comma 3 pi here is basically if we had this unit circle here, and then in polar form, if we had this circle going like this, we're going first negative 4 from our origin. So negative 4 would land us here. And then we're rotating. Let's do it in different colors. We're going negative 4 to this point here at negative 4. And then we're rotating around the unit circle in the positive direction of counterclockwise, 2 pi over 3. So this angle here is that 2 pi over 3. And we want to try and find a repeat of this specific point here. A repeat of that specific point would be any one of these 4. For these top 2 points, we're keeping that radius the same, but then either adding 2 pi to our original radius, or we're subtracting 2 pi from our original radius. If we change the polarity of our radius here to be positive, we just need to add pi to our original radius, or subtract pi from our original radius to find equivalent points here. Between all 4 of these points here, the only one that shows up again is going to be C for question 22. Circle it in black. We're now able to take a look at question 23. For question 23, trying to fix the camera here. You got this camera. There we go. For question 23, we're given this problem of the function of f is given by f of x is equal to 2x squared of this one here. The graph of the following, the graph of which of the following functions is the image of the graph of f after a vertical dilation of the graph of x by a factor of 3. So we know that we have this h of x function that is being affected by f of x, which is affecting f of x by 3 times f of x here. Well, 3 times f of x, which is causing this vertical dilation of a factor of 3, really just is equal to 3 times what f of x is, which is just 2 times x squared minus 4x plus 3. So now we just distribute that 3 to find what h of x is, that transformation. So you know h of x is going to be equal to 6x squared minus 12x plus 9. So now we want to try and find this equivalent equation. So luckily for us, it does happen to be a here. So h of x is equal to 6x squared minus 12x plus 9. Because this is the multiplication transformation of x that results from multiplying f of x by 3. We know that this is correct. We know that this one is wrong because we're not multiplying just the x value by 3, so we don't get this equation. We know C is wrong because we're not adding 3 to it. That would be a vertical transformation, not a vertical dilation, so C is wrong. We also know D is wrong because D is stating that it's an addition transformation of x, results by adding by 3 to the input of x. This is just completely wrong. A transformation of y would not be adding the input to x. That would be a horizontal transformation, so not a vertical transformation here. So D is wrong. Only one value is correct, is A for 23. Moving on to 24, the last 5 problems for this non-calculator active. For question 24, a complex number is represented by the point in the complex plane. The complex number has the rectangular coordinate of -5, 5. Which of the following is an equivalent expression of this complex number using polar coordinates r, theta? So for r, theta, we're going to use a few different ways to try and find what r and theta is equal to. One way to do it is create this trig triangle here, where for this trig triangle, we have this r value, which is just -5 to +5. So we have this trig equation here, where this -5 is our x value, this +5 is our y value, and our r would be this here. Now, some students will do this as their theta value, and this, if we know our x and our y is equal, we know this theta value is equal to 45 degrees, which we know 45 degrees is just pi over 4. However, this is incorrect. Do not do this. This is wrong. Do not do this. The reason why this is incorrect is because we don't want to find what this theta is equal to. Rather, we're trying to find what this outer theta is, because we know theta starts on the right-hand positive side of our x-axis. So it's this overarching theta value that we want to find. Since this overarching theta value is actually equal to 135 degrees, we know 135 degrees is actually equal to our 3 pi over 4. And we're able to find what r is equal to by taking Pythagorean's theorem of this a value of 5 and this b value of 5. So we know r is just equal to the square root of our x squared plus our y squared, which is just going to be equal to 5 squared plus 5 squared, which is just equal to 50 squared. So we know r is going to be equal to 5 to the square root of 2. We know our theta is also going to be equal to 3 pi over 4. And we can create that equation where we know z is going to be equal to r times cosine of theta plus I times sine of that same theta value. This here is our complex plane equivalency. So we know r is equal to 5 pi root 3. We know cosine of theta is just going to be 3 pi over 4. We know sine of theta is just going to be 3 pi over 4 here. And this r would be distributed to both of them here. So we want to try and find that in our charts here. We find pi over 2, or sorry, 5 times root 2 in these two answers of b and d. So we can cross out c and a for these cases. For the difference between b and d here is that d here uses this incorrect negative pi over 4. So we got this one is incorrect. The only value that's correct is going to be b here, because it gives us that correct r value that's distributed to both our cosine and our sine here, and the right theta value, which is the theta from our positive x-axis all the way to that terminal ray for our radius here. For 25 now, we're looking at 25. Moving on still. For question 25 here, the table shows values of a function f at a selected value of x. Which of the following claims and explanation statements best fit this data here? So for this data here, we can just go one by one with these statements. For A, f is best modeled by an exponential function. F is best modeled by an exponential function. F is best modeled by a logarithmic. S is best modeled by a logarithmic. Okay, so A and B is thinking that the function is an exponential function, but C and D think that it's a logarithmic function because the outputs over consecutive equal length input value intervals are proportional. Well, I don't know if this is correct, because if we're looking at x here, x doesn't have an equal length intervals over consecutive equal length input values. These are all different, so we know that this isn't true. So we can probably say that this isn't true. F of x is best modeled by an exponential function because the input over consecutive equal length output values are proportional. Well, we know that an exponential function doesn't have equal length output values that are proportional. That's the description of a logarithmic function. So we know that this function here has to be logarithmic because the outputs are equal length while the inputs are increasing at a exponential rate. So we know that A and B are wrong, and we have to have some logarithmic function. And we know logarithmic functions are only true when the inputs over consecutive equal length output values are proportional. So C is true for 25, meaning that this table here is of a logarithmic equation because our outputs are equal length to our inputs being exponentially growing. If these were reversed, we'd have an exponential function. Another note is that since these are reversed, since our outputs are increasing equal length while our input is increasing exponential, this gives another example on how exponential functions and logarithmic functions are inverses of each other. We're now able to look at question 26. For question 26 here, we're given another table to take a look at here. Question 26 states that the table shows values of h at selected x values. Which of the following claims and explanation statements best fit for this data here? We want to take a look at each of these statements here. For this here, let's actually take a look at the table itself. The table itself has a little bit of an increase in x here. H of x increases. Let's actually take the differences of this here. So the differences is I want to try and find what the second y value minus the first y value give me for all these first differences. In this case here, 85 minus 64 gives me 21. 102 minus 85 gives me 17, so we're kind of going down. 115 minus 102 gives me 13. 124 minus 115 gives me 19. Well, for this thing, since this first difference here isn't constant, I know that this function here isn't linear. So since this first difference is linear, since this second difference here of 17 minus 21 is negative 4, 13 minus 17 is negative 4, 9 minus 13 is negative 4. Since this second difference here is constant, I know the first difference here is linear, making the actual question here quadratic. Now, in the case that this second difference wasn't constant, but rather the third distance was constant, if the third distance was constant, the second distance is linear, the first distance is quadratic, and the actual question is cubic. In this problem, since and because the second distance is constant here, we know the first difference is linear, and we know the output values here are quadratic. So now we want to try and find where this here says that the function is quadratic. H of x best fitting model is linear. Well, we know that's incorrect, so A is automatically wrong. For B, H is best fitted model by a linear function. Well, we know that's incorrect, so we know B is wrong. Taking a look at C here, H is best fitting model is quadratic, so we know this is correct because the rate of change over consecutive equal length intervals is constant. Well, this is incorrect because it's not that the first difference is constant. Rather, it's going to be H is best modeled by a quadratic function because the change in the average rate of change over consecutive length intervals, input value intervals, is constant. It's talking about the second rate of change for part D here, not the first rate of change for part C here. The second rate of change, the average rate of change over consecutive equal length input intervals, that second rate of change, the change in the change is what we want to look at. So for 26, we get the answer as D. Moving on to our last two questions here. For question 27, question 27 states that we're going to let f of x equal 2 times sine of x times cosine of x, and we're going to let g of x equal cosine of x in the xy plane. What are the x coordinate points of the intersections of the graph of f and g between these input variables? Well, really, all we want to say is that for the input sections here, all we want to identify is that these two equations are equal to each other. So we just want to try and say f of x here is equal to g of x here. So we're just going to write 2 of sine of x times cosine of x is equal to cosine of x. Our first thing that we can do is just divide both sides by cosine of x here. and we end up getting that equation where these simplify, and we get 2 times sine of x is equal to 1. We can divide both sides by 2, and we just want to try and find when sine of x is equal to 1/2. We know sine of x is equal to 1/2 in 2 different locations. We know that first location is going to be over here, and we know our second location is going to be on that opposite side, over on this side. And we know sine of x is equal to 1/2, where this theta value is equal to pi over 6. And we also know that the other value here is going to be when it's equal to 5 pi over 6. So we want to try and find at least these 2 values in our problems here. So between 5 pi over 6 and 2 pi over 6. We also want to determine when cosine of value here is equal to 0 in this case, because if cosine of x here equals 0 and cosine of x equals 0 here, then this times 0 equals that times 0, which is that times 0. So the whole entire equation is equal to 0. So the other 2 answers are when our theta value gives us a 0, which is going to be at x equals cosine is going to equal 0 at this pi over 2 and this value of 3 pi over 2. So we want to try and find these 4 answers here. We find these 4 answers in part B, where it's pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. So these 2 values here come from the idea of sine of x equaling 1/2. These 2 values here come from the fact that if cosine of x equals 0, then this whole equation also equals 0 to itself. So our answer here is going to be equal to B. There's a question in chat. I just put them equal to each other and substituted x of x and then made it equal to x, or cosine of x, times 2 sine of x minus 1. Then I put them separately equal to 0 and then solved it out. That would also work if you basically set both of those equations equal to 0 and then solved it out that way. That also gives you a valid for equal equations, because you're solving 2 answers for both of those equations, which give you 4 answers in total. I think that's a very smart way to solve it out, V. Yeah, that's also a good way to do it. Moving on to our final question of 28 here, and then we can have about 5 minutes to burn. For 28, for this final question, the rational function r is defined by r of x is equal to this equation. Which of the following claims and explanation statements about the graph of r is true? Well, let's try and factor out this equation real quick. When we're factoring out this equation here, we want to try and solve out these 2 equations to each other. So we have our r of x is equal to 2 of x to the third minus 5x to the second plus 3 all over x squared plus 2x minus 1. For these equations here, we are able to factor out the denominator here because it's in that quadratic formula, but we can't factor out this numerator here. But for this numerator here, since the numerator's exponent is equal to 3 and the denominator's highest exponent is equal to 4, we have that first case where n is greater than 4. So we're going to have a slanted, oh my God, I can't spell slant, slanted asymptote here. So to find a slanted asymptote, we need to take the long division of these equations here. So to take the long division of these equations here, what we can do is do x squared plus 2x minus 1 of the root of 2x to the third power minus 5x squared plus 3. For that first equation, we're going to multiply this thing by negative 2x, or positive 2x here. So we multiply this equation by 2x. 2x, or x squared times 2x gives us 2x to the third. 2x times 2x here gives us plus 4x here. Now we subtract this from this equation here. So subtract, subtract. These cancel out. These end up adding together to get negative 9. This is x squared. X squared plus 3. We now want to multiply some value to this equation to equal negative 9x. We're going to multiply negative 9 to this equation to match this here. Negative 9 times x squared gives us negative 9x squared. Negative 9 times negative 2x is going to give us negative 18x. Negative 9 times negative 1 gives us positive 9 here. And now we do keep, change, flip. So this here, and then this here. These two 9x's cancel out. This 18x here can't combine with this term, but it can combine with this term. This becomes our remainder is equal to 18x minus 9. So this is the slant for this equation here. So now we can read through our a through d to see which one's the most true for this equation. For a here, let's go from the bottom up. So for d here, the graph of r does not have a horizontal asymptote because the denominator does not have any rational zeros. This is not true. We know a slanted asymptote is a type of horizontal asymptote, so we know d is incorrect. Let's look at c. For c, the graph of r has a horizontal asymptote, which is true because the leading coefficient of the numerator is greater than the leading coefficient of the denominator. That statement doesn't make it true. This statement where the leading coefficient of the numerator is greater than the leading coefficient of the denominator creates a horizontal asymptote, but that isn't why we have a horizontal asymptote. So we know C is false because even though this statement is true that we have a horizontal asymptote, this isn't how it's created. For B here, the graph of R has a horizontal asymptote because the polynomial in the numerator demonstrates the polynomial in the denominator of the input values are of a larger magnitude. We know that's incorrect because the larger magnitude is actually in the numerator, not the denominator. The magnitude has nothing to do with the horizontal asymptote here. The only thing we want to look at is for A here. For A, the graph of R has a slanted asymptote because the polynomial in the numerator is greater than the one in the denominator, and the quotient of the two polynomials is a linear line. So perfect, we know A is going to be right for question 48 here. Since that is it, that is the end of our multiple choice section for our non-calculator problem. For this problem here, we're going to take out our TI-84s. For me, I need to go find my TI-84. It is somewhere inside this classroom. Well, this one's dead. Let me find another TI-84. Hopefully this one's alive. There we go. And then for this TI-84, we're going to have a backup here just in case. But I want to showcase what we should do for our TI-84s to prepare them. Right now, at this point in time, you guys would have a 5-minute optional break for your AP exam. The optional break is given to you on the platform itself of Blue Book. You can take this break, or you can just go right on to the next section of the exam. I am going to take this break a little bit, kind of just preparing for the multiple choice section. I'm going to put in some new batteries to this dead calculator, and then we're going to prepare. Oh, it's not dead, it's just missing a battery. Okay, that makes so much more sense. Sweet. For this, we're going to prepare our calculators during this break time. Because right now we're on the multiple choice section that has the calculator active. All we really want to do is try and make sure that our calculators are cleared. To do that, all you would need to do is press second on your calculators. go to the plus here that says memory right above it. You hit the plus option. When you hit the plus option, you're given this memory here. You want to go down to 7 and then hit enter. And you want to clear all the RAM from this problem here. So yes, want to reset it. So now we're given a clean calculator. The graph doesn't have anything. The y equals doesn't have anything. And then the lists for us also don't have anything with it. Clear that out. To go back to the home screen, you can always use that second and then quit to go back to here. For this section here, we're starting the 40-minute calculator active section. Basically how it works out is you're given about 3 minutes per question for this section of the test. I believe how it's set up is that you'll start this part B of section 1 right after part A of section 1, the normal multiple choice section basically with this calculator active section. So I think that's how it's set up. Honestly, I don't really know, to be frank. I think it makes more sense to do the non-calculator free response section after this, but I'm not in charge of running the actual test, so sucks to suck. I don't know what to tell you guys. Honestly, I think how they set up the AP exam is kind of weird. So you start this exam right after you finish the first 28. That's a typo. That should be question 29 through 40. This may be a typo on yours. If it isn't, awesome. During this 5-minute time too, I would go and get water, take a break, take a breather. We're going to be starting the calculator active section in less than 1 minute, similar to how you guys would for the actual AP exam. Getting into that right headspace and ready to begin. Right, got a little drink of water. Right at the timer here, reading that 4:30, we'll then begin 10-second intro to flip over the page, and then we'll begin the actual question itself. So right now we're about to begin in 5, 4, 3, 2, 1, moving over and split. So this introduction, this is basically what we're going to go through, about 3 minutes per question, and we now begin. For this first question here, we're given question 29. For question 29, we're given this table here. The table presents the values of f at the selected x values. A cubic regression is set up into this A, B, and C, is used to represent this model. What is the value of f of 5 predicted by this cubic model? So to do this, we want to create a equation for this here. So to create this equation itself, we want to go to our stat button. We press that, we press edit, and now we type in the x table of 1, 3, 5, 7, and 8. We now go to L2 here. L2, we're going to type in the y values of 1.423, 23.472, 2121.859, 362.144, and then 547.235. Hit enter. Now we can go back to stats, calculate. We want to do a cubic regression. L1 and L2 is already listed. We just want to try and list the variable in the future. All we would need to do is press the variable button down here, and go over to y variables, hitting enter. Enter again for that y1 in the case that we needed it. But when we calculate it, we end up getting this as our A, B, and our C values. Now, with this y equation inside of it, we actually have the graph itself. But all I really care about is what it equals at f of 5. To do that, I can actually go to second and table set and actually start my table here at 5 here. If I go to second and table, it tells me what x of 5 would be at that problem there. So x of 5 would be 123.4. And if I go to my problem here, 123.4 is going to be our answer for C. We're now going to go on to 30. So for question 30, we're given that the rate of people entering a country music concert at a large arena is modeled by the function of r, where r of t is equal to 0.04 t to the third power minus 0.853 t to the second plus 4.234 of x. The rest of this equation between the interval of 0 to 5. R of t is measured in people per hour, and t is measured in hours since the arena began allowing ticket holders to enter. Based on the model, at what value of t does the rate of people entering the arena change from increasing to decreasing? So we want to graph this equation here and determine when the actual graph goes and changes from increasing to decreasing. So we can graph this equation here in our TI-84 calculators. So again, I'm going to use that trick to clear my data. Second plus 7, 1, 2, and then it clears it all. Now I can go to my y equals, and I can type in this equation here, 0.04 of x to the third power. I can kind of showcase what I'm typing in, to the third power of minus 0.853 of x to the second power plus 4.234 x. No, I need to get rid of all of this. I'm still inside that exponent. So delete, 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 delete. That's a 2. Going over here. There we go. X squared plus 4.234x plus 1.234. And now we can graph this here. But since I'm graphing this here, I can kind of see when it is increasing here at this decreasing rate, and then how it goes right back down. We want to try and determine when it is based on the model, at what value of x does the rate of people entering the arena change from increasing to decreasing. Well, it's changing from increasing to decreasing at the peak of that point there. So we want to try and find what that maximum value is. To do that, we can hit second, calculate, and we can go to maximum right here. We type in maximum, and we want to select this left bound versus right bound. So this left bound, I'm going to put the left side of that peak there. And then this right bound, I'm going to go way over to the right side here. And then select that one. And then my guess is going to be towards this peak here. And then it's going to calculate that the maximum here is at 3.203. So I know at that x value of 3.2, that's when the graph goes from increasing down to decreasing at that x value. And that x value here is located at B. So we can say B is going to be the problem for 30. We're going to move on to 31. For 31 now, we're given this problem of a geometric sequence g of n has known terms of g of 5 is equal to 18, g of 8 is equal to 60.75. What is the value of g12? So we can use that equation where we know g of n is going to be equal to some a value of that, g of k is equal to a of k times r of the k, k minus n. So we can make g8 equal this value here, let's try and figure this out. For your r value, you're able to do g of k minus that, where g of 8 is equal to this k, this original n, so it's a of n. My bad. Okay, so this is my bad. So the equation itself is basically g of k is equal to a of n times r of k minus n, where k is greater than n. So we can say g of 8 is equal to a of n, which is equal to 5 here, which is 18, times our rate of 8 minus 5, where this n and this a of n are connected to each other. We can then say that this whole thing of g of 8 here is equal to 60. So this whole thing is equal to 60.75. So as long as we're saying that this equation is equal to g of 8, which is equal to 60.75 here, we're able to then solve for r here. This n value is an n. This n value is equal to 5 because that was the value that we plugged into here. So this exponent for r is actually equal to 3. So we're trying to solve out this equation, where this equation is just 18 times r to the third power is equal to 60.75. We can divide both sides by 18 to then get r to the third power is equal to 60.75 divided by 18. Take the triple root of both sides. So let's take the triple root of this equation here. So the triple root is going to give me this equation of this math value. So I can go back here. So if I click on math here, this gives me a bunch of options. I can take the triple root for this fourth option here. The fifth option is just going to be any root, so I can just take that fourth option there. And then take the parenthesis of 60.75 divided by 18. And then this gives me 1.5. So then my r value is equal to 1.5. So we're really trying to find g of 12 is equal to 18 times 1.5 of 12 minus 5, where our a of n is still equaling 15. We could use a of 18 in this case here, g of 8 here. We could use 60.75 into this value here, but we would replace that 5 with 8. So I'm going to keep it with this value of 5. We now want to plug this equation into here. So we're going to do 18 times 1.5 to the power of 12 minus 5, which gives us 307.546. And that gives us 307.547. And that is just rounding that third decimal place right here. So we can say for 31, we get the answer of D. And we got the answer of D by first finding R by using this equation here to solve this out. And then once we found R to equal 1.5, we then plugged into this equation to find G of 12. G of 12 is just going to be G of 5, which is 18, times that rate of 1.5 to the exponent of 12 minus 5, which then gave us 307.547. We're now going to move on to question 31. For question 31, we are given the height of the tide is in feet on an intercoastal waterway, is modeled by the function of h, defined by h of t is equal to this equation here, between 0 and 12, based on the model. Which of the following is true? Well, for this model here, we're able to specify that this can basically go between these values here, and from our previous test, we realized that the highest value that this can be for cosine is between -1 and 1. So really, the highest that this could be is 4.3 times 1 plus 7.5, or 4.3 times -1 plus 7.5. So our tide is going to go between 7.8 plus 4.3 and then 7.8 minus 4.3, because that's just how large cosine could be. Doesn't really matter what t is equal in this case. So the highest that it can be is 12.1. The lowest that it can be is like 3.5 here. And we're able to say that for these values here, we can kind of look at this one here. Going from the bottom up, the maximum height of the tide occurs at t equals 6 hours. Well, if t was plugged into 6, that would be pi over 6. Cosine of pi is 0, which would not be the highest, so we can say D is wrong. For C, the maximum height is 12.4. No, it would be 12.1, so we can get rid of this one. The minimum height of the tide is at noon. So if this was 12, we'd end up getting 2 pi. 2 pi is equal to 0. Cosine of 0 is going to be 1. 1 to that is here. So that would give us a maximum height if cosine equal to 1, not a minimum height. So we know A is wrong. Sorry, B is wrong. Let's double check A. The minimum height is equal to 3.5, which it is 3.5, so we know A is correct. Saved a little bit of time for that 32 there. We're able to move on to 33. So now for problem 33, we're given this graph here. The graph of G is shown above. Which of the following intervals gives the domain of the inverse of G inverse, oh my gosh. The domain of inverse G, the inverse of G. So we want to determine between these values here. So all these values is made up of this x and y. This x and y is going to be 2, 9. This one here is going to be 5, 7. We know this value here is going to be 8, 3. So we know that the inverse of this graph is just all these values flipped. So all these values flipped here is going to be 3, 8 is this first point here, 3, 8. This next point of 7, 5, let's go to 7 here. Let's go up to where 5 is. So this one's going to be 7, 5. And this value here of 9, 2, we go to 9 and then to 2, 9, 2. So the inverse of this equation here is this equation here. And we know that the domain for this equation is just going to be our x values, or our x values here are 3 up until 9. So we know that the domain for inverse of G is going to be between 3 and 9. So we look down at our answers here. Our answers, the only one that gives us is for B. And all we've done is just flipped our x and y and found those inverse points. So this point here of 2, 9 is now 9, 2. This point here of 5, 7 is now 7, 5. This point here of 8, 3 is now 3, 8. And the domain is just the x values that we're plugging in. So now we're moving on to 34. Saved a little bit of time there as well. Moving on to question 34. We are well ahead of schedule. For 34, we're looking at this logarithmic graph. I know it's logarithmic because that's the shape of the graph itself. The graph of y is equal to h of x, shown above, is the graph of a logarithmic function. Which equation below represents the inverse function? So the inverse of this function here, of any logarithmic function, has to be an exponential function. So we know that if h of x is equal to that log function here of ln of 3 plus 3 is going to be the y value here. So really, if the x value was 5 and this argument here is 3, we know that the x value has to be inside of this argument. So really, it's just going to be x minus 2 plus 3. So this equation here was derived by this y and this x. We know that x is going to be somewhere inside of the log because it creates that equation there. If this is log or natural log of 3 plus 3 as our y value, well, to get that x value in there as 5, we need to plug in 5 into this equation. So we got natural log of 3 plus 3. So it's from this equation. We now want to try and find the inverse of this equation, where this is going to be equal to x is equal to the natural log of y minus 2 plus 3. And now we solve for our y value. We're going to subtract 3 to both sides, and we get x minus 3 is equal to the natural log of y minus 2. We now raise both sides to the power of e. So now we say e raised to the power of x to the third is equal to that argument of y minus 2. We now add 2 to both sides, and we get e x to the power of x minus 3 plus 2 is equal to y. We know y here is equal to our inverse of this function here. So now inverse of h is equal to this equation. Let's try and find that equation. The equation of x minus 3, so it's not this one, it's not this one, it's not this one. The only one that gives it is for c. So the weird thing for this equation here was identifying that this point of 5 comma ln of 3 plus 3 actually gives us the equation of h of x is equal to the natural log of x minus 2 plus 3, because we know that the x value has to be inside the argument for this log here. Since it has to be on the inside, this natural log of 3, where we plugged in 5, only gives us this function here. So that was the big thing for 34. Moving on to 35 here. For 35, we're given this problem of a complex number is represented by a point in the complex plane. The complex number has a rectangular coordinate of -2, 5. Which of the following is one way to express the complex number using its polar coordinate of r and theta? So we know r and theta are going to give us some trig triangle based off of this -2 and 5. We can make this trig triangle here where our x value is -2, our y value is 5, and our terminal ray goes like this. So we know r here is just going to be equal to our x squared plus our y squared. So r is going to be equal to -2 squared plus 5 squared, which is just going to be equal to 4 plus 25. So we know r is going to be equal to the root of 29. We can solve out this root here in just a second, but right now let's try and solve out the rest of this. We know we can find this theta here, and remember theta is from the positive x-axis here. So this theta is basically going to be solved by finding tangent of theta is equal to that y over x, which is equal to 5 over -2. To find this value here, we can actually use this equation of sorry about that, of theta is equal to the inverse tangent of 5 over -2. And we actually have inverse tangent inside of our TI-84s. So all we really need to type in is second inverse tangent here. Make sure our mode is in radian values and not, make sure our mode is in radian values, not degrees. Since it is, we're able to say the inverse tangent of 5 over -2, 5 divided by -2, gives us this negative 1.19 here. So we know that our value here is going to be negative 1.19 for our theta value. And we're able to say that our problem here is going to be equal to this equation here, where our r value is equal to 29, and then our sine value still has that I here, and then our radian value is -1 or -1.19. So we get our answer of D. All these other equations don't give us those right answers, so that's it. Yeah. Basically, we found our theta here by taking that inverse tangent. We found our r value by doing that Pythagorean theorem. We're going to move on to question 36. For question 36 here, we're given that an alien from the star system was found alive. It crashed in this spaceship, a medical team is monitoring the alien's body temperature and using this function of B given here. Given here. There we go. Now we can see it. So for the question, where T is in time in minutes, since they started monitoring the alien between 0 and 120, which of the following best describes the behavior of B of T when T is equal to 60 minutes? So when T is equal to 60 minutes, let's kind of plug this into this equation here. For this equation, I'm going to hit second, quit. I'm going to erase everything on my TI-84. And then I'm going to type in this equation, 115 plus 9 times cosine. I'm going to add a second parenthesis, 120 times x plus 12 pi, close parenthesis, there we go. So I can do this equation now. We're just typing it in onto graph here to see what it looks like. I don't know if I typed it in right. I think I need to get rid of one of these parentheses. Cosine of 100 of that. Yep, times that. No, I got that right. That plus 12. Let's make sure my window is right. This to here. My y value. I can make this as -1. And I'm going to make my y value here, since t is so far. Let's make this like 100. There we go. Now if I graph it. Oh, whoops, that was my y values and my x values. Oops, windows. My x values here should be like from -10 to 100. My y values here should be like -5 to like +5. Now if I go for the graph here, let's see this. Oh, because we're adding 115 here. So let's do 110 over 120. That way we're higher up on the graph here, and we should see. Oh, okay, so we're like still a little bit low. Let's go to Windows here. Let's go like to 130 to 120. Actually like 110. There we go. So now here's the graph itself. So we know the graph itself is now going down this way. It's going to pop back up in a little bit. I'm going to do a y graph here at 115 just to see how it looks. There we go. And let's change this window here where x is 150. That way we can kind of see like across the whole entire way. So now we want to see specifically when t equals 60 here. For t equals 60, we can plug in 60 where t is. So in this case, this would be 60 plus 12 pi. Close parenthesis, we should get a straight line. Perfect, we get a straight line at that y value. So we're able to say that from t equals 60, where t is time in minutes, since they have started monitoring the alien's body rate, which of the following best describes the behavior when t is equal at 60? Let's try and play around with this equation. Right now, I'm just looking through this. I'm kind of burning some of my spare time here. What I want to try and look at is this given equation as is. So if this is x, let's delete this. I'm going to graph that. This doesn't give like a very sine-looking graph, though. Let's make the x values equal like 1,000. That's not a very, oh, there we go. There is a sine-looking graph. Okay. Make this window here from 130 to like 100. All right, there we go. So now we're given this graph here going up and down. And now I want to see what this line at 105, like this midline here, there we go. Okay, so at this midline here, this is at 115, where the graph itself has basically like this D value that's raising it up. So we know the midline here is at 115. We want to see what happens at x equals 60 minutes. So at t equals 60, let's go to this here. When x equals 60, what do we get? So we're kind of decreasing at that rate there. So for this body temperature here, we can say that for this equation here, that the alien's body temperature is increasing at this decreasing rate here. So we're able to say that at t equals 60, that the alien's body temperature is decreasing at this. So since this is a concave down here, we know this is decreasing at this decreasing rate. So we're able to say that the alien's body temperature here is decreasing at a decreasing rate here. So trying to save some time now, we're able to move on to this next equation for 37. For 37, we need to make up a minute and a half. So for 37, we're going to let k be a polynomial function whose rate of change can be modeled by this function of r, given by r of x is equal to this equation. Based on the model, how many points of inflection does this point have? Well, we know that since this equation is going to be to the third power, we could graph this equation, but we know that since it's to the third power, we're going to have some graph that looks along the lines of this. We know that this graph here is going to have this point of inflection up over to here. So it changes, and then it starts to decrease at this increasing rate, changes one more time right here. So we're able to say that this change in this model here happens at not just one, but at two locations. So we're able to say this happens at B. So this has 2 points of inflection where it changes, where the rate of change, how many points of inflection does this have for k here? We're able to say that it has 2. That's it, because it changes here, and we're now able to save a little bit of time here. Moving on to that next equation of 37. So for 37 now, we're moving on to 38, For 38 now, we're given this question with this table here. The table above gives the selected values of the function k are selected values of t. Which of the following graphs could represent the data value of this semi-log plot, where the vertical axis is logarithmically scaled? What it means to say is that a logarithmically scaled graph on these log plots here is something that looks like part C or part B, where the log plot for this y-axis is an increase in a linear fashion, similar to what we are used to with our x-axis here. So you know it's not A because our y-axis here is not in a log dimension. If we take a look here at C, see how each of these values for each of these row lines increase by a magnitude. This is a logarithmically scaled axis here. So C here looks pretty good. We also want to try and identify if x here is increasing at a consistent rate. So let's try and first just plot these points here at 128. We can actually go to 1 here, and now this is at 10. This next mark is at 20. This is right below where the 30 mark is, so this is at 28. At x equals 2 and 50, we want to go to x equals 2. This is the 10 mark, 20 mark, 30 mark, 40 mark, the 50 mark. So we know this is at 50. At x equals 3 is 85. We go to 3 here. We go to 10, 20, 30, 40, 50, 60, 70, 80. In between the 80 and 90 mark is 85 here. So this is also correct. At 140, we go to the fourth. We go to 100, and we don't go to 200 for that second line. We go right below it. So C here is going to give all of these point values for these log plots here. So we're able to say C is the answer for 38. Moving on to question 34 here. For question 34, for 39 here, not 34, my bad. For 39 here, I'm going to make up just a little bit of time here. For 39, the table above presents values for a function g at a selected value of x. An exponential regression of y equals a times b to the x power is used to model this data. The residual in the model when x equals 5 is 0.627. What is g of 5? So let's just try and find what this equation is using that regression model. So to use that regression model there's also like another way to find this here. So we can also use that second way in a second. Let's find the regression for this here. We turn on our TI-84 calculators, hit second, go to memory, 7, delete all, reset, beautiful. Now go to starts, edit. We're going to do in 0, 1, 3, 4, and 6. At 0, it was 12. At 1, it was equal to 8. This is 8, 5, 3, 0.7. We now go to stats, over to calculate. Let's go to our geometric exponential, our exponential regression, which is also geometric, L1, L2. We can also list our equation here as going to variables, over to functions, y1, calculate. This gives us this equation. This gives us this graph here. But I want to specifically go to second and table start. And I just want to find when this equation is equal to 5 here. So this table start is going to start at 5. I go to second. So I know g of 5 is equal to 1.49. For this regression model. Well, what we're trying to find is what h of 5 is equal to based off of these actuals and this predicted value. So all we want to try and say is for this equation at h of 5, we're trying to find the residuals for this. G of 5 is going to be equal to the value of 1.49. And what we can do is we can find this, this g of 5 here based off of this residual here and this g of 6. So we know that the residual of this value here is going to be equal to our residual of 0.627 is equal to our g of 5 minus our predicted value, which is 1.49. And we can find what our h of 5 is for this problem here by just solving this out here. So we now know our this value of g of 5 is just going to be equal to this plus that, which is 2.11696 for our value. Because this value here was based off of the regression model. So this 1.5 is this 1.49 here. And all I'm using with this equation here is the equation where it's like the residual is equal to the actual value minus the predicted value here. So if we know the residual is equal to 0.6, we're able to plug in that for the residual. We don't know what the actual value of g at 5 is, but we know the predicted value was that negative 1.49. So that's how we found the actual value of our g of 5 here. And this actual value here would be the answer for D. We're now moving on to 40 here. For 40 here, this is our last multiple choice with our calculator. We're going to let g of x equal 2.8 plus 4.5 sine of x. And we're going to let h of x equal cosecant of 1.75 of x in the xy plane. What are the x coordinates of the points of interception for this between there and there? So what we can do is just plot that onto our grid here. I'm going to clear my calculator, all data, reset, y1. For this y1 here, we're able to plot this as 2.8 plus 4.5 of sine of x here. And then for the next value, where h of x is this cosecant, we have to do something weird here. We know cosecant is 1 over sine. So for this, we actually do 1 divided by, it's like a weird thing, 1 divided by sine of 1.75 x here. So there's no like cosecant function in this. We just have to do this like manually. And now when we do the graphs here, we're able to see the graph of that sine kind of passing through this here. And we're able to see this cosecant graph kind of pop up twice here. Yep, 1 there, 1 there, 1 there, 1 there. And we just want to try and find these x values when they happen to cross between this range of x equaling 0 to pi. So I'm going to change my window here. I'm going to make that 0. I'm going to make this equal to pi. And now we really just want to find between these values here when our x value is crossing at that point and our x value is crossing at that point. To do that, we're going to hit second, calculate, and we're going to do intercept. And I'm going to intercept that y1 graph here, intercept that y2 graph there, and then for my guess, I'm going to tab over to this first x value, going way over to here. And then for that guess at that first point there, it gives me the x value of 0.16. Real quickly, I can just double check what 0.16 is. That's one of my answers here, which is this a value. So on my test, since I'm running out of time, I would just automatically type in a into the calculator, or sorry, into the problem. Let's actually find that second value to double check if it's 1.7.6. So I'm hitting second, calculate, intercept, hitting enter. That y1 is for that first graph, that y2 is for that second graph, and now I'm guessing, so I'm tabbing all the way over to that next x value, and I'm going to hit enter. Oh, no, top to the other side. There we go. I'm going to hit enter now, and then for this x value, it gives me at 1.716, so I know that this here is our answer for 40. And that concludes our multiple choice section for our AP test. And we did that a whole 1 minute and 12 seconds ahead of time. So we get this minute and 12 seconds to kind of go through and identify what these values are. I never watched 2.15, but I know the log scale makes the plotted points look linear. Yeah, so there is a question in here for the log scale. So we have a minute here. We can kind of take a look at this before our 5-minute break. We're going to go grab some water. For these log scales here, the idea is, and I know it's kind of hard to see it here. You can kind of see it better in this key that I have. For this key here, we're able to see that the log scale is broken up into these different lines here. Each of these lines are going by that magnitude. So for this log scale, our graph here, our x values increase the normal way, increasing in an equal length, but our y values are increasing with that magnitude. So this here is 1. Our bottom row here for our log graph will never be equal to 0. It'll always be equal to some positive value. So you might see this here equaling like 0.01, but never 0. So that bottom line there is always some positive value. That next line takes the value of this and doubles it. So if this was 1, this value was 2, 3, 4, 5, 6, 7, 8, 9, 10 is right here. And now these lines go by 10. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, and then that next set would go by thousands. So reading a log scale here, the y-axis is now logarithmic. For the question by V here is saying that if we have some function here that is logarithmic, that this table here is logarithmic, then the plotted values here on this log scale look linear. So these log tables give a linear looking graph here when the y-axis is logarithmically scaled. If we're given a table here that is an exponential table, then it will only look linear if the x value was exponentially scaled. So, or sorry, logarithmically scaled. So if the x value is logarithmically scaled and we have a linear graph, then this equation here is exponential. If this equation here is logarithmic and the y value is logarithmically scaled, and then our line here looks linear. Yeah, good question, B. So now we're just taking a look here at our question. Right now we are on this 5-minute break. We still have a break for about 3 minutes in time right now. In this 3-minute time, I'm going to get a drink of some water, and then we're going to begin our free response section that uses our calculator. For this here, I believe this is how the AP exam is set up. We basically have this weird setup where like the multiple choice section is first, both parts are first, and then we do the free response section where we do all 4 free response questions back to back, where I think we start with the multiple choice where it's calculator active. That's the first 30 minutes. Since we only have 2 questions in these 30 minutes, we know that all of our free responses, each question should take no more than 15 minutes per question for our free responses. This is true for a calculator and our non-calculator active questions. If you have any questions about this, you can always let me know. But if not, you guys are good to relax for the next 2 minutes before we begin our FRQs. Just trying to grab a drink of agua. Definitely agua. It definitely isn't Monster, I swear. This crack that you hear is of a bottle, not of a Monster can, I swear. In this 5-minute time, you're able to use the bathroom. I don't know if you're able to bank your breaks together. I know for most of the AP tests, it kind of goes like section by section, and the breaks are optional. So I think you guys can like bank your guys' breaks all together, so to have like a 20-minute break instead of 4 5-minute breaks, or one large 15-minute break and 3 5-minute breaks. I'm not exactly sure how it's given. But I do know that the breaks are not forced, that they are optional for you guys to take. I highly encourage you guys to take your breaks, to take a breather, get you in that right headspace so you can take your AP test as best you can. We'll be starting in less than 30 seconds. How is this? How poor of a microphone quality is this? Is this adequate? I basically just switched microphones. Is this okay? I was talking. Unfortunately, it looks like our microphone died. This is our microphone. It's now at 0%. But if you guys can hear me, awesome. If not, then you're gonna have to read the subtitles. But hopefully, you're able to hear the microphone. Yeah, but I'm a robot now. Dang it. Well, you're all going to be a robot for the next hour, unfortunately. At least the subtitles will be there. This is taken into our time of our FRQ, so I got to do it. So for this here, x is greater than 0. We're going to let the table give values of f of x
is equal to, or is selected at these x values for the function of g of x, which is this here. For part A, actually, while I do this, I can charge the battery. Turn that off. There we go. Okay. So for this here, we're going to try out A here. For A itself, we're going to try and basic question here. For A, we're going to let the function of h of x is equal to g of x, or g of f of x, which is just g of f of x, where x is plugged into g. And we want to find the values of h of 5 as a decimal approximation. And then we want to find the inverse of f of 4 and indicate when that is going to be. So all we want to try and find is h of x here. We're going to take out our tree response notebook, our booklet here. We're going to try and answer it inside of this equation here. So for this, we're basing it off of this equation, which is in the top left-hand corner for this first part here. So for this first part, we're trying to find h of x of g of f of x here, where this is equal to g of f of 5. So when we do f of 5 here, we just want to find when f equals 5, which is going to be 30. So really, we just want to try and find h of 5 here is equal to g of 30. We know g of 30 is going to be equal to this equation here, where it's going to be 30 to the third power plus 11 times 30 plus 23 all over 30 minus 2. I'm going to type that into our TI-84 calculators. 30 to the third power plus 11 times 30 plus 23, which gives me that value. And then I'm going to divide that value by 30 minus 2. And that gives me 976.94. So I'm just going to say h of 5 is equal to 976.892. And then I'm going to add a couple extra decimals here just to make it really clear that I know what it equals. Now for 2 here, I want to try and find what the inverse of f of 4 is equal to. Well, the inverse of f of 4 is when f of x is equal to 4. Well, f of x is equal to 4 here when x equals 3. So we can just say inverse of f of 4 is just equal to 3 here. And this is our answer. Like for 2 here, that's all we need to write for 2. Now we're able to go to part B here. For part B here, we want to look at this part. For part B, we now are reading through. We want to find all of the x values as a decimal approximation for g of x is equal to 4. And then for 2, we want to determine the end behavior of g as x decreases without bound. We want to express our answer using a mathematical notation of limit. So for B itself, we were trying to find what g of x is equal to 4 here. So really, we just want to try to find the inverse of g of x here. So what we can do for this g of x here is, if we go into our TI-84 calculators, if we go to y equals, we clear out these. I'm actually going to go into my y function here, and I'm just going to type in my g of x. So I know my g of x is equal to this equation. I'm going to put a parenthesis here of x to the third power plus 11x plus 23. I'm going to close that off, and I'm going to divide that by parenthesis of x minus 2. And then if I graph this, I'm able to graph it in this area here. I'm going to change my window real quick. Change my window to like -10. the positive 10 in my x, and then for my y's, I like negative 10 and positive 10. So this is my equation here. And then for my equation, I want to find when it equals 4 here. So what I can do is make y equal 4. So this y2, I'm just going to set to 4 here. And it gives me this line. And I just need to find that intersect point, and that gives me my x value. So I can go to second, calculate, intercept between that first curve and that second curve there. My guess is going to be right here, and it gives me my x value as negative 2,4,154. So I'm able to say for this value here, I'm able to say that x is just equal to negative 2.415415. Now for part 2 here, we're trying to find as the limit of x approaches negative infinity, what does g of x do? Well, we know g of x here is equal to this equation here. And for this equation, we really just want to look at what the highest exponent is. This highest exponent is x to the third. So as this x increases to positive infinity, this x to the third is going to increase to positive infinity way faster than this denominator. So this top numerator is going to be a bigger infinity than this denominator, which is going to be a smaller infinity. So we're able to say as x approaches negative infinity, g of x here is going to approach some value. For this down here, as x approaches negative infinity, this negative infinity is going to be some small negative infinity. This x to the third is going to be 3 negative numbers multiplying each other. So it should be a large negative infinity. But since there are 2 negatives being divided out, we know that it's going to approach a positive infinity as x increases negative infinity. We can also look at the graph here. As x approaches negative infinity, this graph is increasing without bound. So now we're able to look at part C here. Part C for this equation itself is going to be that based on the table, which of the following function types best models this for f? Is it linear, quadratic, exponential, or logarithmic? And for 2 here, we want to give a reason for my answer in part C based on the relationship between the change of the change in the output values of f and the change in the input values of f. We want to refer to the values in the table for this reasoning here. For this equation here, we're able to plug this into our TI-84 and do a couple of models here. So let's actually go to stats. Let's go to edit. Let's type in this table. Let's do 1, 2, 3, 4, 5. And then we can go to -6, -3, 4, 15, and 30. And now for this equation, we're able to kind of hit to our stats here, go to regression types, go to quadratic regression, 2, 1, 2, 1, go to variables, type in the windows, functions. Let's just put this into y3 just so it doesn't cover up anything. And we get this quadratic equation of 2, -3, and -5 for our A, B, and C. So we're able to say that our f of x here is equal to 2x squared minus 3x minus 5. And since this here is a quadratic model, we can say that a quadratic model is the best fitting model because the linear and logarithmic residuals have a pattern. Exponential has a domain error. So the quadratic function is the best fitting model because a linear or logarithmic regression would cause the residuals to form a pattern, and then the exponential model has domain errors, and the domain errors come from the fact that we are getting these negative values from our x values, which are positive here. We know it's not exponential because of the domain errors. We know it's not logarithmic or linear. So we create the residual plots would have a pattern. So we know this is a quadratic model. For 2 here, we're able to say that the average rate of change of the quadratic function over consecutive equal length input intervals can be given by a linear function. F is best modeled by a quadratic function since the rate of change of the average rate of change is constant. So all we're really showcasing is that for this equation here, if we look at the first and second differences, for this first rate of change from -6 to 3 here, we're adding 3. From 3 to 4, we're adding 7. From 4 to 15, we're adding 11. From 15 to 30 here, we're adding 15. From 3 to 4 here, we're adding 4. From 4 to 11 here, we're adding 4. From 4 to 15 here, we're adding 4. So the first difference is linear. The second difference here is constant. So from this here, we're able to state that because the average rate of change of a quadratic function over consecutive equal length input values or input intervals can be given by a linear function of f is best modeled by a quadratic function since the rate of change of the average rate of change is constant. So since the rate of change, the second difference of the first difference is constant, we know it can be modeled by a quadratic graph. And so we're good to move on to our second FRQ. For this second FRQ, we're now looking at this equation here. For this equation here, for number 2, we're given this table here for 2. The table above shows the population of bacterial of B of T presented in a blood sample of a patient prior to prescribing a medication of infection. The table gives values of the number of bacteria present in the sample over a 6-hour period. The level of bacteria in the blood sample can be modeled by the function of B of T is equal to A times B to the T power, where B of T is the population of bacteria in the blood sample for any hour of T since the initial sample reading. In part A here, use the data points of 1, 76 and 2, 98 given the data here, to write two equations that can be used to find the constants of A and B in the expression of B of t. I'm going to find what those values are for A and B. For this problem now, all we really want to try and do is we're given, oh, where'd my notes go? Oh, there's my notes. For this problem here, we are already given that we want to try and find what B of t is equal to, where it's A times B of t for those 2 points. So we can plug in those 2 points of 1, 76 and 2, 98 into this equation here to write out those two equations. And all we're really doing is plugging in this 1 into where t is, and then this 76 into where b of t is. So that first equation is just going to be equal to 76 is equal to a times b to the first power. And then that second equation is just going to be 98 is equal to a times b to the second power. So these two are the equations that I would use to solve it out. Now for 2 here, I'm actually going to solve out a and b for both of those questions. For this here, I can actually write out that since a times b is equal to 76, this does give me that option that b is equal to 76 divided by a, or a is equal to 76 divided by b. So it gives me that option of what I want to plug in to this equation here to solve it out. So then you know b is squared here. If I plug in this a where b is in the denominator, it's going to cancel out one of those b's here. So I can kind of save some time. So I can do 98 is equal to 76 over b times b squared. For this here, this b cancels out that exponent. So we get 98 is equal to 76 times b, where b is just the quotient of 98 divided by 76. And that there is just going to be 98 divided by 76. So we know b is equal to 1.289473.6. Now we could plug this into any one of these equations here and just solve for a here. I'm going to plug this b into this equation and then solve for a. To plug it in just a little bit more precise, I know that b is exactly this function here. So if I plug in this expression into where this is, I'll get a more accurate value of a. I'm going to show that real quick. So 76 divided by this here gives me this decimal, but 76 divided by 78 divided by 76 gives me this decimal here. It's only slightly different at the very end, but technically speaking, this second answer is more accurate than this first answer here, because I use the actual operation inside of it. But I'm still able to say that a in this case is equal to 78.93877. And then for these decimals here, if you're confident with the first 3 decimals here, I would just go with the first 3 decimals where you're rounding that third decimal. If you list these back decimals as incorrect, they'd be wrong for this question. So just make sure all your decimals are as correct as you can get. So now we're able to move on to part B for this question. For part B for this question here, it has 3 different parts. We're going to try and use the given data to find the average rate of change of the bacteria in the blood sample for the time of t equals 1 to t equals 4 hours. We're going to express our answer as a decimal approximation. We want to show the computation that led to this answer here. Second, we want to interpret the meaning of the answer in context of this problem here. And then in 3, we want to consider the average rate of change of b from t equals 6 to t equals h. So everything past this data collection, where h is greater than 6, are these average rates of change less or greater than the average rate of change from t equals 0 to t equals 4 hours found in b of I? Explain your reasoning. Use the explanation. Should include a reference to this graph of this b of t. So let's first try and find 1. So we know for 1 here, we're going to use that equation of f of b minus f of a all over b minus a, this average rate of change equation here. We know we're going to plug in those values of t of 4 and t of 1. We go back to our table here. T of 4 is equal to 154 here. So we're able to plug in 154 minus, we know t of 1 is 76, so we plug in 76 here, all divided by 4 minus 1, which is just going to be 78 divided by 3. 78 divided by 3 is going to be 70 divided by 3, 26. And it's going to be 26 bacteria per hour. So since it's going to be 26 bacteria per hour, it helps us with part 2 here. Part 2 is asking us to explain our answer for part 1 in context. For part 1, we can say that for every hour between t equals 1 to t equals 4, the infection is not treated, the bacteria in the blood would increase at a rate of 26 bacteria per hour. So for every hour of 1 is less than or equal to 2, which is less than or equal to 4, that the infection is not treated. The bacteria in the blood will increase by increase at a rate of 26 bacteria per hour. And then we could be a little bit more specific here and just say that on average, the bacteria increases at 26 bacteria per hour over the 3-hour period. Now for part 3, we're again going to try and describe past this data set here of past 6 hours here. We're going to try and describe it in the context referring back to the graph itself. So for this part here, the average rate of B from t equals 6 to t equals h hours is going to be greater than this average rate of change here because B has an exponential growth. The graph is going to be concave up. Therefore, the average rate of change in the bacteria per hour are increasing over equal length input values at a decreasing rate. So we're going to say the average rate of change for B from t equals 6 to t equals h hours is greater than the average rate of change for 1 is less than t, which is less than 4, because B is an exponential graph. Therefore, the average rate of change in bacteria per hour are increasing over equal length input values. Now we're going to look at part C here. For part C, we only have 3 minutes left. For this here, we're going to speed right through it. So we want to try and answer for which t-value of t equals 4 or t equals 12 hours should the medical staff have more confidence when using this model of t. You want to give your answer based on the context of this problem. Well, since t equals 4 was given to us as this collected value here, this is actual real-world data for t equals 4. We don't actually know what would happen at t equals 12 here. That would be that predicted data past this table here. So we just want to say that the medical staff can be confident using the model for t equals 4 hours. The regression model is appropriate for 1 to 6 hours. However, for t equals 12 hours, there is not enough information about the patient or treatment in order to extend the model beyond the given data set. So we can say that the medical staff can be confident using the model for t equals 4 hours. The regression model is appropriate for 1 is less than t, which is less than 6 hours. However, for t equals 12 hours, there is not enough information about the patient / treatment in order to extend the model. And that there is where we're going to close it off for this equation here. So we have a lot of writing for this in context equation here. So make sure you feel pretty confident in writing out these terms a little bit better than I've written here. Try and write cleaner than I did here. Ideally, you would write more legibly. But that there is the end of our free response 2. So at this point, you would take another 5-minute break between your 2 free response sections. So right now we're a little bit early for 30 seconds. For this 30 seconds here, I'm going to attempt to plug in the other microphone and see how that goes for these 5 minutes. I'll be back just 1 second. See if I can do this here. All right. Well, it looks like I cannot get the other microphone to work, so I'm just going to use the desktop microphone. And we're going to go right through our break here and just begin the last section of our FRQ. For this last section of our FRQ, we're taking a look at FRQ 3 and 4. For FRQ 3 and 4, we're taking a look at the non-calculator section. For these non-calculator sections, we're given this FRQ 3 here. For this FRQ 3, we're on this problem now for FRQ 3. We're looking at an emergency vehicle is parked next to your bedroom wall with a light on. The top of the vehicle is traveling a circular path that completes one rotation every 18 seconds. The diameter of the light is 2 feet. When the light is closest to the wall, is 8 feet from the wall, and t equals 0 seconds. At point B is the closest to the bedroom wall. It is shown in the diagram. So point B here, reverse diagram here. The light rotates around the base on the top of the vehicle at a constant speed. The distance of B to your bedroom wall is periodically increasing and decreasing. The sinusoidal function h models the distance between B and the wall in feet as the function of t in seconds. For part A here, the graph of h the graph of h and its dashed midline for 2 full cycles is shown. The 5 points of F, G, J, K, and P are labeled on the graph. No scale is indicated. No axes are present. We want to locate each of these 5 points based on the information told to us. Oh, I see what's messed up with our timer here. Okay. So for our timer here, it didn't have a 5-minute break time. Okay, that's what it is. So we're now going to look at our 3 here. So for 3, we want to try and write in a few of those key parts there that tells us are like points across this whole area here. So for those key parts there, we're able to note that the full path itself, the diameter of the light is 2 feet. So we can say that this light here is 2 feet for this section. And then the wall is 8 feet away from the closest. So we know this here is going to be 8 feet. We know that one rotation here takes 18 seconds here. So since one rotation takes 18 seconds, we know that the distance between our F graph here and our P graph here is going to be 18. So we know that the period is going to be equal to 18 seconds. We're now able to say that this is 18 seconds, and we're at when the light is closest to the wall, it is 8 feet from the wall here. So we know this is 8 feet. We know this diameter is 2 feet. We know this diameter here is equal to 2 feet. So you know that this furthest distance here is going to be 10 feet from the wall here. So this is going to be the furthest part here is 10 feet. The closest is going to be 8 feet. We know that our maximum is going to be 10. Our minimum is going to be 8. So for these values here, we know our y value here is going to be 10. We know our y value here is going to be 10. We know our minimum value here is going to be 8. Since these midpoints between these ones here are exactly like in the middle of these two, we know these y values are going to be 9. We know these y values are going to be 9. And we don't know exactly what these x values are, but we know the distance from F to P here is going to be 18 seconds. We can also write that the max here is going to be equal to 10 feet. We know the minimum here is going to be equal to 8 feet. Kind of keeping this as notes for us here. We now want to try and find when that first point occurs. We're able to say that this first point occurs at 0 seconds. Point P or point B is the closest to the bedroom wall here. So if this here is the closest to the bedroom wall at t equals 0 seconds, we could make this value here equal to 0 here. Or since I know that if that t was equal to 0 here, and it was the closest at t equals 0, I know that j here, it returning to the closest, would be 18 seconds. So I can either make this here equal 0 seconds, or it completing one full rotation back to it as 18 seconds. I like the value of this being 18 because then all of these x values here will be positive. Instead of making this 0 and all these are negative and all of these 0 are positive, I'm going to make j here equal to 18. As a reminder, I could also make j equal to 0 here. My y values wouldn't change. The only thing that would change is these other x values. If I know the middle point is 18, I know this upper point here would be 27, or in the case that I made that 0, this upper point here would be 9, 10. And over here, since my j value is 18, I know my value here is going to be 9. I made my j value 0, then this value over here would be negative 9, 10. And since I made this 27 and 9 here, it has a period of 18. I know my g and my k value are just going to be halfway between 9 and 18, or negative 9 and 0 here, which in my case is going to be 13.5 or negative 4.5, 9, or k here, which is going to be 22.5 in between 18 and 29, or in between 0 and 9 here would be 4.5, 9. So any one of these points here would work, but you'd have to keep all the points the same. So we made this the closest, or this is one full cycle. We'd have 18 or 0, but the y values are still the same. We've now labeled all these here. Now we're able to move on to part B. For part B here, we want to find h. So the function of h can be written as h of t is the a of cosine of b times t plus c plus d. We want to find the values of a, b, and c and d here. I'm going to find those values in part A and then rewrite them in part B. That way I can use my information from up here. For my information here, I want my period information to find b. We know b is going to be equal to 2 pi over p here. And we're able to say 2 pi over 18 gives me a b value of pi over 9. We know our amplitude here is going to be our maximum minus our minimum divided by 2. In this case here, we get 10 minus 8 divided by 2, which is just 2 over 2, which is 1. 1 makes sense because our midline is at 9 and it only goes up 1, and our midline is 9, it only goes down 1 to 8 here. We know our d value is also going to be that maximum plus our minimum all over 2, which is going to be 10 plus 8 over 2, which is 18 over 2, which is 9. We also know 9 is that midline here, or our y value is 9. So you know d is equal to 9. In this case here, since our maximum is starting at f here, and cosine starts at a maximum, this is the value that we'd use as our c value. Since c itself has shifted our maximum so far over, we can say c is equal to negative 9. So now we want to grab these pieces of information and rewrite them here, where we can say a is equal to 1, where b is equal to pi over 9, and we're able to say c is equal to negative 9, and d is equal to positive 9. With that said, we're able to write our h of t. Our h of t is going to be equal then to 1 times cosine. So we can just write cosine of our bracket here of pi over 9, parenthesis t plus 9 here, because our c value is being subtracted, so a double subtraction is plus 9, parenthesis, close bracket, plus 9 again, and then this here would give us our equation. In the weird case that we use these other values here for our cosine function, we would end up getting this other h of value, where like h of t is equal to negative cosine of pi over 9t plus 9. So for this red version of the graph would be for this bottom version of the points here. So you can also solve it that way. We're also now looking at part C now. For part C itself, we want to try and solve out this little mini multiple choice question where C here is refer to the graph of H in part A here. The t coordinate of G is T1 and the t coordinate of J is T2. On the interval of T1 to T2, which of the following is true about H? So T1 is going to be G, T2 is going to be J. So we're looking at part here. We're looking at this part from G to J here. We know G to J here is going to be positive, so it's not a negative part of the graph because the y values are so positive. So we can get rid of our C and D option because we know H is positive. And we want to say if it's increasing or decreasing. In this case here, it is decreasing. It's not going up. So we know B here is going to be the most right answer in our case. So in our answer here, we would write choice B, H is positive and decreasing on T1 to T2. I think you could just write B in this section for I here, but I really want to be explicit that this is the whole equation itself that I'm saying. So now we're going to look at 2 here. For 2, it was asking us to say on the interval of T1 to T2, describe the concavity of the graph of H and determine whether the rate of change of H is increasing or decreasing. What we know H here is concave up and decreasing. So we know that this is a decreasing at an increasing rate because it's concave up. We're able to say that the graph of H is concave up on the interval of T1 to T2. So the rate of change of H on the interval is increasing. So we're able to say that the graph of H is concave up on the interval of T1 to T2. So the rate of change of H on the interval is increasing. That's it. So we basically just want to say that the graph of H is concave up on that interval there, so the rate of change of H on the interval is increasing. We're in a little bit clearer. Technically, we would have like another 40 or so seconds left, but because I messed up the timer now, we're going to move on to that final part here of our FRQ3. For our FRQ3, let's go to here for FRQ4. Moving on to here. There we go. So FRQ4, we're now back on track, and now we're given 15 minutes for our FRQ4. Our FRQ4 is this final question of right here, where we're going to try and, so unless otherwise specified, the domain of the function of x is assumed to be set of all real numbers of x, for which f of x is a real number. The angle measured of the trigonometric functions are assumed to be in radians. The solutions to equations must be real numbers. Determine the exact value of any expression that can be obtained without a calculator. For example, log of 2 of 8, cosine of pi over 2, and inverse sine of 1 can be evaluated without a calculator. In this case here, this would equal 3. In this case here, this would equal 1. In this case here, this would equal 0 and 2, or 0 and pi. These are types of problems you can solve without a calculator. 3, unless otherwise specifies, combine terms using algebraic method and rules of exponents and logarithms where applicable. For example, 2x plus 3x can be combined together to get 5x. 5 to the second times 5 to the third can be combined together to get 5 to the fifth. Or x to the fifth divided by x to the second can be rewritten as x to the third. And ln of 3 plus ln of 5 is just going to be ln of 15, 3 times 5. We want to simplify and rewrite all of these problems here. For each part of the equation, mark your work that leads you to your answer. So you want to write out your work for these problems. In part A, we want to solve for g of x is equal to 2. We're going to find the x values and the domain for g of x here. For 2, h of x is equal to -1 for all the values between this interval here. So for part 1 here, all we really want to try and write out is that equation where we're trying to solve out g of x is equal to log, write this out here, where this is equal to log base 3 of 4x minus 7. We want to set this equal to 2. So we want to try and solve out this equation here. So we know that we can just raise to the power of 3 on both sides to get rid of that log there. So raising to the power of 3 simplifies out that log there, and we're left with the argument of 4x minus 7 is now equal to 3 raised to the power of 2, which is equal to 9. We then add 7, and get 4x is equal to 16. Divide by 4, and we can say that x is equal to 4 here. I'm not just going to box it in because I'm that confident. And then for I here, we now just want to try and find h of x, which is equal to 2 sine of x, where this is equal to -1. So we want to try and solve for this x value here. First, we're going to divide by 2. We're going to find sine of x is equal to -1/2. Well, sine of x is equal to -1/2 only in 2 locations on the unit circle. In the unit circle itself, I know it's going to be equal here and here. For these angle values, I know that sine is equal to 1/2 here at theta, or in this case, x, is equal to 7 pi over 6, or its corresponding theta value of 11 pi over 6. I'm so confident I'm actually going to box this in as well. We're now looking at part B here. For part B, we now want to try and look at these two equations, j of x and k of x. So for one, we want to rewrite j of x as an expression in which secant of x appears once and no other trigonometric function are involved. For two, we want to rewrite k of x as a single natural log without negative exponents in any part of the expression. Your result should be in the form of an expression. So let's try and rewrite f of x and k of x here. So j of x and k of x. For one here, we're given j of x is equal to cosine of x plus sine of x times tangent of x. And eventually we're trying to write it out so that secant of x is by itself. So really, I'm going to play around with this tangent here. Tangent usually tells me something about these two problems here. So I'm going to rewrite tangent as that quotient of sine over cosine. So this is equal to cosine of x plus sine of x times sine of x over cosine of x here. Let's multiply this out so we get sine squared over cosine there. So then we get cosine of x plus sine squared of x over cosine of x. Well, let's actually combine these terms together. Since we're combining these terms, we need to make this term here have the same denominator as this term. So let's multiply this whole term by cosine of x so that they're in the same fractional denominators. So cosine of x times cosine of x is just going to give me cosine squared of x over cosine of x plus sine squared of x over cosine of x. And all I really did was I multiplied this value by cosine over cosine so that the fractions have the same denominator. I'm going to now rewrite this where I have now cosine squared of x plus sine squared of x all over cosine of x. Well, I know cosine squared plus sine squared is just equal to 1. So this gives me 1 over cosine of x. I know 1 over cosine of x is actually equal to secant. And that there would be my solution. So I'm basically showcasing all of these steps here with that little arrow directed over there. Now I'm going to solve out 2. For 2 here, I'm trying to find that k of x here is equal to the natural log of x minus 5 minus the natural log of 2, natural log of 3 minus 3 natural log of x plus 1. So my first goal is to try and bring these coefficients that are in front of these natural logs here as exponents into these problems here. So I can say that this is equal to the natural log of x minus 3 minus ln of 3 squared minus the ln of x plus 1 to the third power. I know that any subtractions here are just going to be quotients of these. So really what we're doing here is we're saying x minus 5 divided by 3 squared, which is 9, divided by x plus 1 here. So really what we're getting is the natural log of x minus 5, this first argument here, divided by 9 times this division is going into this 5, or this x minus 5. So this x plus 1 to the third power is in the denominator of this argument here. So x plus 1 to the third power. And this here is what k of x is simplified to. We do want to specify a small domain for this problem here. We know that our problem here can't be anything that is less than 0. So we know that the domain in this problem here is where x is greater than 5. Because if x was less than 5, we've had a negative number, and we can't take a negative natural log. So this is our answer for part 2 of part B. We now want to look at the final part of the final free response of the final question of this mock exam. For part C here, the function m is given by m of x is equal to sine 2x minus root 3 of cosine x. We're going to find all the values in the domain of m that yields an output value of 0. So really we're going to set m of x here equal to 0. So we really just want to try and find m of x is equal to 0. We know m of x here, if this is going to, oh, come on, there we go. M of x here, we know m of x is sine of 2x minus root 3 of cosine of x is equal to 0 here. We now want to try and solve this out here. To solve this out, what I can actually do is separate out this sine of 2x here into that product of 2 sines. So we know sine of 2x, or doubling that input value, actually is equal to 2 times sine of x times cosine of x. This sine of 2x is just equal to 2 times sine of x times cosine of x. That's an equivalency for doubling your input. And then we just drop down the rest of this, minus root 3 of cosine of x is equal to 0. Well, now that we have cosine of x in both of these terms here, we can pull it out. And we can say cosine of x is equal to 2 times sine of x minus root 3 is equal to 0. So now we have these two terms here. If this term becomes 0, times this term, we would get 0. If this term is 0, then times that would also give us 0. So now we have these two equations here where we have cosine of x is equal to 0 and 2 times sine of x minus root 3 is equal to 0. We want to try and solve out these equations. Well, cosine of x is equal to 0 in only 2 locations. We know those 2 locations there are going to be when x is equal to pi over 2 directly up on the unit circle. So when we're at this value here and this value here, So we know when x is equal to pi over 2 or when x is equal to 3 pi over 2. So those are our first two answers there. We can solve out this equation. So we're going to do 2 times sine of x is equal to the root of 3. Divide by 2, divide by 2. Sine of x is equal to the root 3 of 2. When we know that only occurs at two locations on our x-axis or on our unit circle, that is going to occur here at this value and this value here, where sine is only equal to root 3 over 2, where x is equal to pi over 3, or its corresponding angle of 4 pi or of 2 pi over 3 on this side here. So these here are for x values, where sine of 2x minus root 3 of cosine x is equal to 0. And for this problem, let me read it real quick. Find all the input values in the domain of M that yield an output. So we want to write an equation for this here. For these for these four equations here, we just want to rewrite these equations in terms of each other. We also know that since these equations here are a pi away from each other, so they repeat a pi, we can say that this general form here is going to be x is equal to pi over 2 plus pi times k, where k is equivalent to any integer. And then for these two equations here, we want to write out these two equations as x is equal to pi over 3 plus 2 pi times k, where k is equivalent to any integer, or x is equal to 2 pi over 3 plus 2 pi times k, where k is equivalent to any integer. So those three equations would give us all of the values where this is true here. This equation here is secretly like two equations doubled up, but since our doubled up is a pi away from each other, is repeat over a pi. These two equations only repeat every 2 pi around the unit circle. So our equation here is 2 pi times that k value, which satisfies that answer here, where we want to find all the input values in the domain of M that yield an output value of 0. That there is the end of our mock exam. We fully finished like a minute early for this exam itself. If you have any questions at all when it comes to the mock exam, the free response, the calculator active, the non-calculator, please let me know either by typing a comment on this post here, emailing me, or by asking me on Monday, the day right before our exam. Other than that, thank you very much for tuning in. I'm going to let the clock run out until 12:55. Yeah, thank you very much for tuning in for our mock exam. It was a lot of work this year. I'm incredibly proud of all of you guys. I am going to deeply miss it, many of you. I think this was an amazing class, and I'm really happy that we were able to turn it around towards the end of the year. Each and every one of you guys makes me deeply proud to be a teacher, and I'm so honored to have worked with you this year. I cannot wait to see what you guys get as a result. I'll be grading all of your FRQs this summer, so it's going to be pretty intense. But yeah, I'm incredibly proud. I'm deeply humbled and honored to have you all as students, and I look forward to working with you guys in the future. Take care. Have a lovely one. I'm going to let the stream run just until the end of our speed run timer in case there's any questions. But if not, have a great rest of your day. Bye. You guys have done great. I'm proud of you. Bye. just grabbing papers. Once our speed run ends at 3 hours, 12 minutes, and 55 seconds, our stream will end. And that's it. That's all she wrote. Make sure you guys sleep well. Make sure you eat right before your exam. Our exam starts at 8 a.m. on Tuesday. Make sure you know what room you're going to. You do not need to go to first period. You can go directly to the location that you're taking your AP exam. Keep that in mind. There is no check-in for your other classes. Once you take your AP exam, you are good to go and just leave campus. We don't really expect you guys to do a bunch of classes after your exam. So once you finish your exam, you guys are good to head out. Other than that, that's kind of it for the total of this class and the exam itself. I'm predicting, honestly, you guys to be doing amazing with it. So I'm not too worried about the exam. I'm sure some students are worried about their exam, but I'm not worried. You guys are all smart. I believe in you guys. Make sure your calculator's charged. You've had breakfast. You slept 8 hours. And you're in the right headspace. Cool. Other than that, I'm just rambling. I'm going to end the stream in 2, 1. Timer has stopped. We finished our class on Monday's classes. We'll be hanging out. So take care. Have a good one. Thank you for tuning in.